Our galaxy isn't just drifting through space as a single isolated island of stars. It's surrounded by a swarm of much smaller companions. These tiny galaxies orbit us like moons, locked in a slow gravitational dance that has been going on for billions of years. They don't look impressive compared to giants like the Milky Way or Andromeda, but without them, the universe would be unrecognizable. Some of them are being pulled apart as we speak, leaving behind long rivers of stars across the sky. Others may be time capsules from the dawn of the cosmos, carrying within them the secrets of how the very first galaxies formed. To study them is to peel back the layers of our own galactic history and to glimpse the future of the Milky Way. What counts as a galaxy? Setting the boundaries. When we look at the night sky through a telescope, we see countless collections of stars. Some are vast, stretching across hundreds of thousands of light years, while others are far smaller and faint. To the human eye, they can all look similar, points of light grouped together in the dark. But for astronomers, there is an important question hiding here. What counts as a galaxy? At first, it seems simple. A galaxy is a huge group of stars. But when you look closer, the line between a galaxy and a cluster of stars becomes much harder to draw. The deeper astronomers have peered into the cosmos, the more confusing this boundary has become. A galaxy is a system, a living environment of matter, gas, and invisible forces. For many scientists, one of the key traits that separates a galaxy from a simple cluster is gravity. In small clusters, the gravity binding the stars together comes only from the stars themselves. But in galaxies, there is an extra element, dark matter. This mysterious material makes up most of a galaxy's mass and acts as a kind of invisible glue. Dark matter forms a halo around the galaxy, giving it the strength to pull in gas, shape the orbits of stars, and even resist the pull of nearby galaxies. If you strip away this unseen halo, the structure quickly falls apart. For this reason, many astronomers argue that a true galaxy must show signs of being supported by dark matter. Larger galaxies often pull on their smaller neighbors, tugging at them with powerful tidal forces. These forces can stretch and twist a smaller object until it breaks apart completely. Star clusters caught in the orbit of a giant galaxy are often shredded over time, their stars scattered across the sky. But dwarf galaxies, even tiny ones, often remain intact for billions of years. Their dark matter halos protect them, helping them hold together despite the immense gravitational tides. This endurance is one of the reasons astronomers treat them as real galaxies rather than clusters. But not every system fits neatly into this rule. Some of the faintest galaxies ever discovered seem to blur the boundary. Ultra-faint dwarf galaxies, for instance, contain only a few thousand stars, less than some star clusters. Yet they behave differently. They spread their stars over a wider area and move in ways that suggest the presence of far more mass than we can see. The only explanation is that they are dominated by dark matter. In this way, galaxies that look small and fragile can still count as galaxies because their invisible scaffolding is so strong. Another trait that often separates galaxies from star clusters is the ability to create new stars. In many galaxies, clouds of gas collapse to form new generations of stars, a cycle that can continue for billions of years. Star clusters, on the other hand, are usually born in a single burst. After their first round of stars ignite, they quickly burn through their gas. With no fuel left, they cannot make new stars. This difference in star formation history is crucial. It makes galaxies evolving ecosystems, while clusters are more like fossils of a single event. If you look at the chemical makeup of stars, this contrast becomes even clearer. Galaxies show a wide variety of chemical fingerprints, because new stars form from gas enriched by older ones. Clusters, by comparison, show a much simpler record, locked in at birth. Still, even here the edges blur. Some large star clusters, like Omega Centauri in the Milky Way, show signs of chemical complexity that resemble galaxies. In fact, some scientists think Omega Centauri might actually be the remnant of a dwarf galaxy stripped of most of its stars and gas long ago. This possibility shows just how tricky the boundary is. Objects can change over time, moving from one category to another. A galaxy torn apart by tidal forces can leave behind a star cluster. A cluster that holds more mass than expected might secretly be the leftover core of a destroyed galaxy. The way stars move within a system tells you about the gravity holding it together. In clusters, the motions of stars can be explained by the visible mass alone. But in galaxies, the stars move too quickly for the visible matter to keep them bound. Something else, dark matter, must be there, tipping the balance. By studying these motions, astronomers can decide if a faint object in the sky is truly a galaxy or just a cluster. Even with all these criteria, there are still debates. Some astronomers argue that insisting on dark matter as a requirement is too restrictive, because in certain cases, galaxies can lose much of their dark matter through interactions. Others suggest that star formation is not the best marker, since even galaxies can run out of gas and stop making new stars. What remains constant, though, is the idea of complexity. A galaxy is not just a group of stars stuck together. It is a system shaped by both visible and invisible matter, built to last and capable of evolving across cosmic time. If we draw the line too narrowly, we risk overlooking small but important systems that may hold clues to how galaxies first formed. If we draw it too widely, we risk blurring the unique processes that make galaxies different from clusters. The faintest galaxies ever found, barely visible against the dark, push the definition to its limits. Are these ghostly systems truly galaxies, or are they something in between? The answer is still unfolding. This uncertainty reflects a larger truth about science. The universe does not always fit neatly into the boxes we create. Our definitions are tools, meant to help us understand, but the cosmos constantly challenges them. In the case of galaxies, the challenge is particularly sharp, because these systems are central to the structure of the universe. They are the homes of stars, planets, and perhaps life itself. Understanding where galaxies begin and end helps us understand how the universe itself is organized. The realm of the small, dwarf galaxies explained. If the great spirals and giant ellipticals are the lords of the cosmic stage, dwarf galaxies are their quiet companions. They may not dazzle the eye with sweeping arms or brilliant cores, but they are everywhere. In fact, when astronomers count the number of galaxies in the universe, the majority are dwarfs. These are the lightweights of the galactic family, small and faint, sometimes so faint they are almost invisible against the dark. Our galaxy contains around 200 to 400 billion stars, depending on how you count them. A dwarf galaxy, in contrast, may have only a few billion stars, or even fewer. Some of the tiniest examples contain just a few thousand stars. To put that in perspective, a large star cluster inside the Milky Way can contain hundreds of thousands of stars. A typical dwarf might span a few thousand light-years compared to the Milky Way's 100,000. Some are so compact they would fit comfortably inside a single spiral arm of a large galaxy. Others are puffed up and spread out, their stars scattered thinly across space. Despite these differences, one thing unites them. Dwarfs lack the grandeur of large, well-structured systems. They don't have the neatly wound spiral arms we see in galaxies like Andromeda, nor the smooth, glowing balls of stars seen in giant ellipticals. Instead, they often appear irregular, lopsided, and messy. Their stars are unevenly distributed, their gas clouds ragged, as if they were never finished being built. This irregular look is partly the result of their weakness. Because dwarf galaxies have less mass, their gravity is not as strong. That means they have a harder time holding onto their stars, gas, and dust. A close encounter with a larger galaxy can distort them, leaving behind a warped shape. Many dwarfs are satellites of bigger galaxies, and their appearance shows the scars of these interactions. Even so, dwarf galaxies are not just leftovers or scraps. They are thought to be some of the first building blocks of the universe. In the early cosmos, before giant galaxies formed, small clumps of gas and dark matter gathered into dwarfs. Over time, many of these merged together to form larger galaxies. In this way, the great spirals and ellipticals we see today are the product of countless smaller systems combining over billions of years. Some dwarfs survived this violent process intact, orbiting as satellites around their bigger cousins. These survivors may carry valuable clues about what galaxies were like in the earliest times. Not all dwarfs look the same. Astronomers divide them into categories based on their shape and behavior. Some dwarfs, called dwarf spheroidals, are diffuse and faint, often containing very few stars spread across a large volume. They show almost no gas and little to no star formation, making them ghostly, dim objects. Others, called dwarf irregulars, are more active. These are clumpy, gas-rich systems where new stars still form. In fact, dwarf irregulars can shine brightly in certain regions, with glowing clouds of hot gas lit up by clusters of young stars. There are also dwarf ellipticals, which are smoother and rounder than irregulars, but smaller than the giant ellipticals seen elsewhere. Compared to large galaxies, dwarfs tend to be poor in heavy elements. Stars create heavy elements through nuclear fusion and supernova explosions, but in dwarfs, many of these enriched materials escape. With weak gravity, they cannot hold on to the blast of a supernova as easily as large galaxies can. Over time, this means that their gas remains relatively primitive, more like the early universe. Astronomers can thus study conditions similar to those that existed long ago, before galaxies like the Milky Way were fully developed. Despite their low star counts, dwarf galaxies seem to be dominated by dark matter. In fact, pound for pound, they often contain more dark matter relative to visible matter than the giants do. This is why they can survive at all, even when they are so faint. Studying these halos helps scientists learn about the nature of dark matter itself. Some of the smallest known dwarfs have been called dark matter laboratories because of how sensitive they are to its invisible presence. The Milky Way is surrounded by dozens of dwarf galaxies. The most famous are the large and small Magellanic clouds, visible to the naked eye in the southern hemisphere. These two irregular dwarfs are gas-rich, full of young stars, and currently interacting with both each other and the Milky Way. Their distorted shapes and star-forming regions are evidence of this gravitational dance. Closer in, our galaxy also hosts a population of tiny spheroidal dwarfs, some of which were only discovered in recent years through careful surveys of the sky. These faint companions are so diffuse that they almost vanish into the background, yet they are still galaxies in their own right. Other large galaxies also have retinues of dwarfs. Andromeda, for example, is accompanied by more than 30 known dwarf galaxies, forming a miniature system of its own. In fact, dwarf galaxies are so common that astronomers believe there may be far more waiting to be discovered, especially in regions of the sky that are harder to observe. Many of them could be hiding at the edge of detectability, faint clouds of stars that require the most powerful telescopes to spot. Though they are small, dwarf galaxies can still make a big impact. When a large galaxy absorbs a dwarf, it can stir up star formation, add fresh gas, and alter the larger system's structure. Our own Milky Way shows signs of having merged with dwarfs in the past, leaving behind trails of stars in its halo. Some of the globular clusters in our galaxy may even be the remnants of ancient dwarfs stripped down to their cores. In this sense, dwarfs are both the seeds of galaxies and the fuel that continues to shape them. There is also a mystery tied to dwarf galaxies known as the missing satellites problem. According to computer simulations of dark matter, galaxies like the Milky Way should be surrounded by hundreds, maybe thousands, of small dwarf companions. Yet when astronomers look, they find far fewer. Either we are not seeing the faintest ones, or something about the way galaxies form is different from what the models predict. This puzzle remains unsolved, but every new dwarf discovered brings us closer to an answer: the hidden majority of galaxies in the universe. They shine like lighthouses in the dark, while the dwarfs are more like faint sparks scattered everywhere. Their small size and low brightness make them nearly invisible in wide surveys of the sky. To detect them requires deep, careful searches, and often, even then, they remain little more than faint smudges against the blackness. Astronomers have learned to look for these hidden galaxies in clever ways. One approach is to search near larger galaxies, where dwarfs often cluster as companions. Around our own Milky Way, the large and small Magellanic clouds are the easiest to see. But fainter satellites, like the Draco dwarf or the Ursa minor dwarf, are so dim that they are only visible through detailed surveys of star motions and brightness. As telescopes have improved, more of these faint companions have been discovered, and each new find suggests that there are many more waiting to be revealed. Another method is to use wide-field digital surveys that map the sky in detail. In recent years, projects like the Sloan Digital Sky Survey, or SDSS, have uncovered dozens of ultra-faint dwarfs by picking out subtle clumps of stars that move together. These discoveries have shown that the universe is teeming with small galaxies, and yet astronomers are convinced that we have only found a fraction of them. When scientists run computer simulations of how galaxies form, they begin with the growth of dark matter halos. These halos form from the gravitational pull of dark matter, drawing in gas and creating the conditions for stars to form. In the models, small halos form first, then merge to create larger ones. This process naturally produces an enormous number of small galaxies, far outnumbering the giants. It is a bottom-up picture of cosmic growth, where the small arrive before the big. Evidence from our own local group supports this view. The local group, which includes the Milky Way Andromeda and a collection of smaller galaxies, is dominated by dwarfs. Beyond the two giant spirals, nearly every other member is a dwarf galaxy. Some are irregulars, while others are spheroidals, barely visible even with modern instruments. This small corner of the universe offers a snapshot of the broader truth. Wherever there are galaxies, dwarfs are the most numerous. A dwarf galaxy with only a few million stars produces far less light than a spiral with hundreds of billions. By the time that dim light has traveled across millions of light years, it becomes almost impossible to detect. Our telescopes must compete not only with distance, but also with the faint glow of background stars, cosmic dust, and even the light pollution of Earth itself. Many dwarfs blend into the cosmic background like shadows. Detecting them requires long exposures and sensitive instruments, and even then, astronomers may only identify them as small overdensities of stars, rather than clear shining galaxies. If most galaxies are dwarfs, then they may hold most of the information about how galaxies form and evolve. Large galaxies like the Milky Way have undergone many mergers, collisions, and bursts of star formation that blur their history. Dwarfs, being smaller and simpler, often carry a more direct record of what happened billions of years ago. The universe is often described as a web, with galaxies strung along filaments of dark matter separated by vast voids. If dwarfs dominate the numbers, then these filaments are even richer than we once thought. Each faint dwarf adds weight to the cosmic scaffolding, helping us map the invisible skeleton of dark matter that holds everything together. Without accounting for them, our picture of the universe is incomplete. Looking ahead, astronomers expect the hidden majority to step into the light as new tools become available. Telescopes like the Vera C. Rubin Observatory, with its ability to survey wide areas of the sky in great depth, are expected to reveal hundreds of new dwarfs around the Milky Way and beyond. Space-based observatories freed from Earth's atmosphere will also peer deeper, detecting faint smudges of light that ground-based telescopes cannot. The missing satellites problem. In the late 20th century, astronomers began to run large computer simulations to understand how galaxies formed. These simulations used the known laws of physics and the idea that dark matter makes up most of the universe's mass. Out of this came a striking picture. Galaxies like the Milky Way should not be alone. They should be surrounded by hundreds, maybe even thousands of small dark matter halos, many of which ought to host dwarf galaxies. In other words, our galaxy should have a massive swarm of tiny companions, like bees around a hive. But when astronomers looked into the sky, they saw something different. Instead of hundreds, only a few dozen satellite galaxies were known. This mismatch between prediction and observation became known as the missing satellites problem. The problem stands out because simulations reproduce large-scale cosmic structure with impressive accuracy. The cosmic web, the clustering of galaxies, the growth of large halos all match what we see in the universe. But at small scales, around galaxies like our own, the numbers don't add up. The dark matter halos that should exist in great numbers seem to be empty. Either they exist but do not host galaxies, or our understanding of dark matter itself is incomplete. At first, some astronomers wondered if the problem might be simple. Perhaps the missing satellites were there but just too faint to detect. As digital surveys and deeper imaging came online, more faint dwarfs began to appear around the Milky Way. The Sloan Digital Sky Survey, for instance, uncovered many ultra-faint dwarfs in the northern sky. Later surveys like the Dark Energy Survey found more in the south. Each discovery chipped away at the missing satellites problem. Yet even today, the total number of known dwarfs around the Milky Way is in the dozens, far fewer than the hundreds predicted. If the satellites are not simply hiding, another possibility is that the simulations assume too much about how gas and stars behave in small dark matter halos. In theory, every halo should be able to collect gas and form stars, but in practice, many may fail. In the early universe, powerful radiation from the first stars and quasars may have blasted away gas from small halos before they could form galaxies. Later, supernova explosions inside early dwarfs could have blown out much of their remaining gas, shutting down star formation permanently. If this happened often enough, then many dark matter halos might be dark themselves, containing no stars at all, invisible to telescopes. In this view, the missing satellites aren't truly missing. They are there, but they never lit up. Another angle is that the physics of dark matter itself may not be what we think. The standard model of cosmology assumes that dark matter is cold, meaning it moves slowly compared to the speed of light and clumps together easily. Cold dark matter predicts lots of small halos, just the kind that lead to the missing satellites problem. But what if dark matter behaves differently? If dark matter is warm, moving faster in the early universe, it would smooth out the smallest structures and prevent as many dwarfs from forming. If it can also interact with itself in subtle ways, it might further erase the smallest halos. These alternatives remain speculative, but the missing satellites problem is one of the strongest motivations to explore them. The Milky Way satellites are not the only place to test the issue. In Andromeda too, the numbers fall short of predictions, although it seems to have slightly more companions than the Milky Way. Looking at clusters of galaxies provides another test. In larger environments, small galaxies seem to be more abundant, but the smallest predicted dwarfs are still hard to find. Across all scales, the puzzle repeats itself. The missing satellites problem blends two different mysteries. On the one hand, it might be about how galaxies form. Maybe star formation shuts down in small halos more often than we thought. On the other hand, it might be about dark matter itself. Maybe the invisible substance we rely on in our models has properties we have not yet uncovered. The challenge is to separate these two. If we can detect more ultra-faint dwarfs, we might confirm that many small halos really do host galaxies. If we cannot, then we may need to rethink the very nature of dark matter. In recent years, progress has been made by carefully mapping the sky and looking for stellar streams. These streams show that some satellites have come and gone. This means that the Milky Way's current census of dwarfs is not the whole story. Over billions of years, many more may have existed, only to be absorbed or destroyed by the host galaxy. If so, then the simulations may not be entirely wrong. Still, even accounting for faintness and destruction, the gap between theory and observation remains wide. Some estimates suggest that the Milky Way should have at least a few hundred satellites. Unless our surveys are missing nearly all of them, we are left with a serious tension. This is why the missing satellites problem is often described as a test of the standard model of cosmology. If our picture of the universe is correct, then the missing satellites must be out there. The missing satellites problem forces astronomers to test the limits of their models and to look more carefully at the smallest scales of the universe. Whether the answer lies in faint galaxies, we have not yet seen. In physics we do not yet understand, or in a mix of both, the puzzle helps drive research forward. How dwarf galaxies are discovered. One of the earliest ways to find a dwarf galaxy was to stumble across it by accident. A careful astronomer scanning photographic plates of the sky might notice a faint smudge that didn't quite match the appearance of a known star cluster. These early discoveries were often uncertain because the difference between a loosely bound group of stars and a true galaxy is difficult to see at a glance. But as instruments improved and digital imaging replaced film, astronomers began to design surveys that specifically looked for such faint, smudge-like objects. Wide-field surveys became an essential tool, allowing the entire sky to be mapped with enough detail to capture even the faintest structures. The SDSS was one of the most important steps forward. Using a dedicated telescope in New Mexico, it scanned large parts of the sky with high precision and produced one of the most complete maps of stars and galaxies ever made. Within this vast dataset, researchers began to notice overdensities of stars, tiny patches where more stars appeared than expected. These overdensities often turned out to be dwarf galaxies. What was once overlooked in the night sky was suddenly visible thanks to the careful statistical analysis of enormous amounts of data. Star counts became one of the primary methods of dwarf galaxy discovery. Instead of looking for a glowing patch of light, astronomers would search for regions where stars seemed unusually concentrated. A dwarf galaxy might only reveal itself as a slight bump in the star count graph, but with enough data and careful analysis, these bumps are the fingerprints of hidden companions. This method is particularly powerful near the Milky Way. Our galaxy contains billions of stars, which makes the background sky crowded and noisy. But when a dwarf galaxy is present, the stars in that patch of sky often share similar properties, such as color or brightness. By filtering for stars that appear older, redder, or dimmer, characteristics typical of dwarf galaxy populations, astronomers can pull a faint galaxy out of the overwhelming glare of the Milky Way. Ultra-faint dwarfs, discovered in the past 2 decades, contain so few stars that they are on the edge of what we might consider a galaxy at all. Detecting such objects requires not just powerful telescopes, but clever techniques to filter signal from noise. The faintness of these dwarfs means that if you were standing inside one, you might not even realize you were in a galaxy at all. The stars would be too sparse, the night sky not much different from what you would see on Earth. To uncover such fragile systems, astronomers now rely on deep surveys that go far beyond the sensitivity of earlier projects. The Dark Energy Survey, carried out using a 4-meter telescope in Chile, has been one of the most successful at finding new dwarf galaxies. By imaging large areas of the southern sky to extreme depths, it revealed dozens of ultra-faint dwarfs orbiting the Milky Way. Modern instruments also make use of motion to confirm discoveries. A random patch of stars could be mistaken for a dwarf, but true galaxies have stars that move together, bound by a shared gravitational field. By measuring the tiny shifts in starlight caused by motion, something that requires highly sensitive spectrographs, astronomers can test whether a faint group of stars is truly a galaxy. If the stars show random, unconnected motions, the group might be a cluster. But if they move in a way that suggests they are bound together by invisible mass, then the presence of dark matter reveals it to be a galaxy. The Hubble Space Telescope has been used to resolve individual stars in suspected dwarfs, allowing astronomers to measure their ages and confirm their nature. With its sharp vision above Earth's atmosphere, Hubble can distinguish details that ground-based telescopes often blur together. Future telescopes promise to revolutionize the search further. The Legacy Survey of Space and Time will repeatedly scan the sky, providing a dynamic map that can reveal not only faint galaxies, but also how they change over time. The process of discovery is slow, patient, and ongoing, but with every faint smudge revealed, the hidden structure of the cosmos becomes a little clearer. Mapping the Milky Way's neighborhood, Around the Milky Way swarm dozens of smaller companions. These satellites vary enormously in appearance, structure and size, yet together they paint a picture of how diverse the galactic family truly is. The most obvious members of this family are the Magellanic Clouds. The Large Magellanic Cloud, or LMC, is bright enough to be seen with the naked eye from the southern hemisphere. With roughly 30 billion stars, it is by far the largest of the Milky Way's companions. Its smaller sibling, the Small Magellanic Cloud, contains only a few billion stars, but still easily outshines nearly all the other dwarfs in our neighborhood. Both are irregular galaxies, lacking the clear spirals or smooth ellipses of giants like the Milky Way. They are filled with gas, actively forming new stars, and display regions of glowing nebulae where stellar nurseries flourish. These two galaxies are the heavyweights of the Milky Way's entourage, and their mutual interaction with each other and with the larger galaxy makes them among the most studied objects in the sky. Beyond them lies a retinue of smaller, more fragile systems. These are the dwarf spheroidals, so faint that they remained hidden until quite recently. They are ghost-like, often containing only a few 100,000 stars spread over large volumes. Unlike the Magellanic Clouds, they hold little or no gas, and new star formation is absent. Examples include the Sculptor, Fornax, and Carina dwarfs, each one a dim collection of ancient stars orbiting tens to hundreds of thousands of light-years away. Still closer to the Milky Way, some satellites creep almost unnoticed through its halo. The Sagittarius dwarf, discovered only in the 1990s, is being torn apart as it plunges through the disk of our galaxy. Long stellar streams arc across the sky, marking its remains as it is steadily digested. The Canis Major dwarf, another low-mass companion, is similarly in the process of dissolution, its stars smeared into arcs that wrap around the Milky Way's outskirts. These galaxies are reminders that the boundaries of a galaxy are porous. The census of satellites extends even farther, stretching hundreds of thousands of light-years from the Milky Way's center. Some companions, like Leo I and Leo II, orbit at great distances, almost on the edge of the galaxy's sphere of influence. Despite their remoteness, they still remain tied to the Milky Way's gravity, tracing slow orbits over billions of years. Each of these systems adds a different chapter to the galactic family history, some showing evidence of ancient bursts of star formation, others displaying a smooth population of only old stars. The satellites can be grouped not just by their brightness or size, but also by their type. The gas-rich irregulars like the Magellanic Clouds are rare but spectacular. The gas-poor spheroidals are numerous, faint and widely dispersed. Ultra-faint dwarfs push the definition of a galaxy to its edge. Together, they outline a spectrum of companions. Another important way to look at the neighborhood is by distance. A few dwarfs lie very close, only tens of thousands of light-years from the Milky Way's center, deep inside the halo. Others drift far beyond, at distances closer to 1 million light-years, where the pull of the Milky Way competes with that of Andromeda. The distribution is not even. Clumps of satellites appear in certain regions, possibly tracing the remnants of larger systems that broke apart long ago. Some researchers even argue that the satellites may be arranged in vast plains or streams, although whether this is real or just an illusion is still debated. The Magellanic Clouds are giants with billions of stars each. The classic spheroidals contain millions of stars. The ultrafaints may have only hundreds or thousands. Yet across this wide range, all are considered galaxies. By charting the Milky Way's neighborhood in this way, astronomers build a picture of not just what exists today, but also of the history of interactions. The bright irregulars may represent fresh arrivals, not yet stripped of their gas. The faint spheroidals may be the remains of systems long battered by the Milky Way's tides. Some of the ultrafaints may be fossils of the very first galaxies that formed in the universe, preserved in miniature form. Each companion offers a clue to how galaxies grow. Stellar streams, the ghostly trails of consumed galaxies. If one could strip away the glare of the Milky Way's disk and look only at the halo, the sight would not be smooth or empty. Instead, it would resemble a spider's web woven from stars, thin and delicate, but stretching over immense distances. These are stellar streams. They are not whole systems anymore. They are the shredded remains, their stars pulled free and stretched into long arcs. The Milky Way's halo is filled with them, like a cosmic graveyard of companions that could not resist the pull of the giant at the center. Imagine a small galaxy falling into the Milky Way. Its stars move together, bound by their mutual gravity. But as it circles the larger galaxy, the tidal pull begins to stretch it. Stars on the far side feel a slightly weaker tug, while those on the near side feel a stronger one. Over time, the system unravels, its stars peeling off and forming tails. These tails follow the original orbit, wrapping around the galaxy in long trails that can span hundreds of thousands of light years. What was once a single, coherent body becomes a dispersed ribbon, impossible to separate from the greater halo except by careful observation. One of the most famous of these is the Sagittarius stream, the debris of the Sagittarius dwarf galaxy. Its stars form arcs that wrap almost entirely around the Milky Way. Other streams, like GD1, Orphan and Palomar 5, are equally striking, though often fainter. Some are linked to disrupted dwarf galaxies, others to globular clusters that were pulled apart. Each one is a fossil record written in the positions and motions of stars. By studying them, scientists can retrace the orbits of vanished systems and reconstruct the history of the Milky Way's growth. Detecting them is a challenge. Many are faint, lost in the sea of background stars. But surveys that map the sky in detail have revealed more and more of them. What once seemed invisible became patterns that could be traced and measured. As they orbit the Milky Way, they are shaped not just by visible matter. If the dark matter halo were smooth, the streams would be graceful and unbroken. But some appear clumpy, torn in places where the stars have been deflected. These disruptions may reveal the presence of invisible dark matter clumps, remnants of smaller halos that never formed into galaxies. In this way, stellar streams act like detectors, mapping the unseen structure of the galaxy's dark matter through their distortions. Even after a dwarf galaxy is completely consumed, its stars do not vanish. They continue to move together, sometimes for billions of years. Over time, the stream thins and disperses, blending into the halo until it can no longer be distinguished. But before that final dissolution, it offers a glimpse into a violent past. Some astronomers describe the Milky Way's halo as an archive, with stellar streams as the documents within it. Taken together, they show that the Milky Way grew layer by layer. Without streams, this history might be hidden. The Orphan stream is one example of a particularly evocative case. As its name suggests, the parent system that created it has been almost entirely destroyed, leaving behind only the ribbon of stars. Astronomers can measure the motions of these stars and deduce the orbit of the lost system, but the original dwarf is no longer identifiable. It has been erased, leaving only its trail. Palomar 5, on the other hand, still has a surviving core, a globular cluster that continues to shed stars into a long pair of tidal tails. Observations show that it is slowly dissolving, and in time, it too will vanish, leaving only its stream as a memory. Some streams are twisted and folded, reflecting complex histories. A system might orbit many times, each pass stretching new stars into the halo. Overlapping arcs can make the structure seem chaotic, but careful study reveals the rhythm of repeated disruption. These patterns not only map past interactions, but also allow astronomers to test models of the Milky Way's formation. In a sense, stellar streams are evidence of continuity. The dwarf galaxies and clusters that birthed them no longer exist in their original forms, yet their stars live on, circling the galaxy as part of a new whole. The Milky Way's brightness, its richness, is due in part to these absorbed companions. Without them, it would be smaller, less grand. The Large Magellanic Cloud, a satellite rivaling a galaxy. With its broad spread of stars, active regions of star formation, and noticeable spiral-like features, the LMC looks more like a scaled-down spiral than a minor satellite tagging along. For observers in the southern hemisphere, it stands out to the naked eye, visible as a cloudy patch in the night sky that has been known to humans long before telescopes were invented. Its brightness and structure make it one of the most remarkable examples of a companion galaxy, and one of the most studied as well. Its estimated stellar mass is around 1/10 that of the Milky Way, which means it is enormous by the standards of satellite galaxies. It also appears to contain a large halo of dark matter, which allows it to hold itself together even as it passes close to the Milky Way. That stability has allowed it to keep an organized structure rather than being torn apart. Astronomers can trace the way its stars form patterns across the sky, with clear evidence of spiral arms and a central bar of stars, much like those seen in galaxies far larger. This is one reason why the LMC occupies such an unusual place in the galaxy family. It seems to straddle the line between being a true independent galaxy and a satellite bound to our own. Star formation is happening at a rapid pace compared to many other nearby galaxies, including our own. One of the most famous star-forming regions in the entire sky, the Tarantula Nebula, sits within its bounds. This nebula is a sprawling, glowing cloud of gas and dust, where new stars are being born in great numbers. The brightest and most massive stars known have been found inside it, shining with such power that they illuminate the entire region. Supernovae have also been observed within the LMC, their explosions lighting up its skies. In 1987, the closest supernova visible to Earth in modern times occurred in the LMC, giving astronomers an unparalleled chance to study how such an event unfolds in detail. That single explosion, known as SN 1987A, remains one of the most important astronomical events of the past century, and it happened right inside this remarkable galaxy. Many small galaxies have lost their gas, but the LMC still has large reserves of hydrogen, providing the raw material for stars to keep forming. This supply of gas may be partly due to its size and partly due to its orbit, which has only recently brought it close to the Milky Way. Some studies suggest that the LMC is on its first close pass around our galaxy, meaning it has not yet had time to be fully disrupted by the Milky Way's tidal forces. If true, then we are catching the LMC at a special moment in its history, just as it begins to feel the grip of a larger neighbor. For years, astronomers assumed the LMC had been circling the Milky Way for billions of years, completing many orbits. But more recent measurements of its velocity suggest it may be moving too quickly for that to be the case. Instead, it might have only recently fallen into the Milky Way's sphere of influence, perhaps bringing along its own smaller companions. If that is correct, then the LMC is more like an intruder than a long-term partner, a separate galaxy that is only now becoming a satellite. The LMC's gravity is strong enough to tug on the Milky Way itself, shifting the motions of stars in our galaxy's disk. Some astronomers believe that the Milky Way's dark matter halo may even be distorted by the pull of the LMC. The interaction between the two galaxies has also left behind a vast trail of gas called the Magellanic Stream. This ribbon of material stretches across much of the sky, stripped from the LMC and the small Magellanic Cloud by gravitational forces. The stream may one day rain down onto the Milky Way, fueling new bursts of star formation in our galaxy. If the Milky Way was smaller or the LMC farther away, we might classify it differently. The fact that it lies in this grey zone shows how nature resists simple categories. Galaxies, like all cosmic objects, exist on a spectrum. For humans on Earth, the Large Magellanic Cloud has long been more than a scientific puzzle. Navigators and storytellers in the Southern Hemisphere wove it into their traditions. Today, with telescopes and satellites, we can explore its depths in detail, but it still carries that same sense of wonder. It is a galaxy that is both near and foreign. The Small Magellanic Cloud, torn between giants. The Small Magellanic Cloud, or SMC, is an unusual companion. It doesn't have the neat spiral arms of a disk galaxy or the smooth glow of an elliptical. Instead, it looks disordered and lopsided, more like a patch of scattered light than a carefully built system. Over time, the picture that has emerged is that the SMC is not a galaxy living in calm isolation. It is caught in a tug-of-war between two giants, the LMC and the Milky Way. Its strange appearance is a direct result of being pulled in different directions at once. The SMC is located about 200,000 light-years away from Earth. That's close enough in cosmic terms to make it one of the nearest galaxies outside the Milky Way. It contains only a few 100 million stars, far fewer than its larger sibling. This means the SMC is a small galaxy even by dwarf standards. Because it is so close, astronomers can watch how its stars, gas, and shape are changing as forces from the outside pull on it. Instead of being a clean sphere or disk, it stretches in an irregular pattern, with regions of dense stars separated by gaps of empty space. One area looks like a main body, while another looks like a detached wing, as if a piece of the galaxy has been stretched away. This structure is believed to be the result of tidal forces. The two Magellanic clouds are close enough that they form a pair, orbiting the Milky Way together. For billions of years, they have likely been circling each other while slowly spiraling inward toward our galaxy. Their mutual gravity binds them, but it also distorts them. The SMC, being the lighter of the two, is the one most obviously bent out of shape. Astronomers think the wing-like extension of the SMC is the result of a close encounter with the LMC, which stripped away part of its material and left it trailing. Another clue to the SMC's struggles comes from its gas. When telescopes look at the Magellanic clouds in radio light, they reveal a massive river of gas stretching away from them. This Magellanic stream arcs across the sky for hundreds of thousands of light-years. It is thought to have been pulled out of the SMC and LMC during their repeated encounters with each other and the Milky Way. The SMC, with its lower mass, has lost more of its gas than the LMC. This is one reason why the SMC looks patchy today. The tidal pulling has also influenced how stars are born inside the SMC. Normally, star formation in a galaxy depends on the availability of cold gas clouds. In the SMC, astronomers see evidence of starbursts in its recent history. Some regions contain clusters of very young, bright stars, indicating that gravitational stress has sparked new activity. At the same time, other areas appear depleted, as if the fuel for star formation has already been swept away. This uneven pattern fits well with the picture of a galaxy caught in an ongoing struggle. Because it is nearby, scientists can measure its stars and gas in detail. They can even track how some of its stars are moving through space using precise instruments. These measurements show that the SMC is not simply drifting quietly around the Milky Way. Instead, it has a complex orbit. The irregular shape could be a sign that it is still adjusting to life under the Milky Way's pull. Astronomers debate whether the SMC and LMC will eventually merge with each other before being absorbed into the Milky Way. If they merge, the combined system may resemble a larger dwarf galaxy, though still far smaller than the Milky Way. If instead the Milky Way's gravity tears them apart first, the SMC may eventually dissolve, leaving its stars scattered across the sky as streams and clusters. Either way, its current irregular form shows that it is already well on the way to being reshaped. Like its larger sibling, it appears as a fuzzy cloud of light visible to the naked eye on clear nights. Sailors once used it for navigation, and observers noted its unusual hazy appearance centuries before telescopes revealed its true nature. The SMC is a living example of what happens when small systems are caught between giants, reshaped by forces they cannot escape. The Magellanic Bridge and Stream, tidal scars in the sky. The Magellanic Bridge is a structure of stars and gas that physically connects the LMC and SMC, almost like a tether between them. For a long time, the clouds were thought of as two separate neighbors drifting near the Milky Way. But observations in the 20th century revealed that they were bound together, and the gravitational pull between them had drawn material out of the SMC and into the space between the two. When astronomers looked more closely, they saw streams of young blue stars stretching across this gap, showing that star formation had even taken place in this bridge, sparked by the compression of gas as it was torn out and reshaped. The Magellanic Bridge is a snapshot of motion, the material caught in the middle of being traded and stripped during a long ongoing encounter. Even more striking is the Magellanic Stream. Unlike the bridge, which sits between the clouds, the stream extends far beyond them, wrapping across the sky behind the pair as if they were dragging a comet's tail. This stream is made of hydrogen gas, stretched out over more than 600,000 light-years, longer than the Milky Way itself. It is faint and invisible to the naked eye, but radio telescopes tuned to the frequency of neutral hydrogen can detect it clearly. The Magellanic Stream tells the story of repeated tidal encounters between the clouds and the Milky Way. Each time the dwarfs swing around, some of their gas is pulled loose, left trailing behind in space. Over billions of years, this has created a ribbon so vast that it circles much of the southern sky. Gas is the fuel for star formation, and when galaxies lose too much of it, they stop making new stars and slowly fade away. The stream suggests that the Magellanic Clouds cannot keep their material forever. In time, much of what once belonged to them will fall into the Milky Way, feeding its halo and perhaps sparking bursts of new star formation within our own galaxy. A fascinating aspect of these tidal features is that they are not uniform. The bridge and stream show knots, clumps and filaments, as if the forces pulling on them were not steady but chaotic. Some parts of the stream appear denser, while others fade into nothing. The reasons for this are still being explored. Part of it comes from the uneven gravity of the Milky Way, which does not pull evenly across the clouds. Part may also come from the interaction of the stripped gas with the thin atmosphere of hot plasma that surrounds our galaxy, known as the circumgalactic medium. As the Magellanic gas moves through this halo, it is stretched, twisted, and even eroded, leaving behind a ragged pattern rather than a smooth arc. In the distant universe, astronomers often see galaxies merging or tearing at each other, but those are usually so far away that only the broadest structures are visible. Here, in our cosmic backyard, we can map the stripped gas almost cloud by cloud, star by star, and use it to test our models of how gravity and tidal forces work over millions of years. The bridge shows us what happens when two dwarf galaxies pass close enough to exchange matter, while the stream shows what happens when those same dwarfs fall into the sphere of a much larger host. Together, they are like a laboratory of cosmic dynamics, visible not with exotic equipment, but with radio dishes and patient mapping. With instruments like the Australia Telescope Compact Array, the Parkes Radio Telescope, and space observatories such as Gaia, the details of the bridge and stream are becoming sharper. By tracking the motions of stars within the bridge, researchers can reconstruct the history of when the clouds last passed closest to one another. By measuring the chemical makeup of the stream, they can determine whether the stripped gas came mostly from the small Magellanic Cloud, the large, or a mix of both. These questions matter because they tell us not only about the fate of the clouds themselves, but also about the long-term flow of matter into the Milky Way. Sagittarius Dwarf Galaxy, a victim of cannibalism. The Sagittarius Dwarf Galaxy is a fragile system caught in the grip of the Milky Way's enormous gravity, and unlike the Magellanic Clouds, which still hold together, Sagittarius is already being torn apart. It is a living demonstration of galactic cannibalism. Astronomers first recognized the Sagittarius dwarf in the 1990s, and even then, it was already showing signs of distress. Its stars stretched out in long, faint streams that wrapped around the Milky Way like a necklace broken apart and scattered across the sky. Instead of being a neat, compact ball of stars like many other dwarfs, Sagittarius was elongated and shredded, caught in a process that has been going on for billions of years. The fact that it was discovered so late shows just how faint it had become. Much of its original mass is no longer bound to the galaxy itself, but has been stolen and spread throughout the Milky Way's halo. The story of Sagittarius begins with its orbit. Unlike a quiet companion that circles far away, this dwarf plunges directly through the Milky Way's disk on a path that guarantees repeated encounters. Each pass subjects it to tidal forces. As Sagittarius swings past, The Milky Way's gravity pulls harder on its near side than its far side, slowly prying stars and gas away. With every orbit, it loses more of itself, peeling away layer by layer until only a small core remains. This violent process leaves scars that are visible across the night sky. The stellar streams from Sagittarius wrap around the Milky Way like a ribbon wound around a globe. These streams are not just beautiful, they are scientific treasure troves. They act as test particles, tracing the shape of the Milky Way's gravitational field. By mapping where the stars go, astronomers can infer the unseen distribution of dark matter that gives the Milky Way most of its mass. In this way, the death of Sagittarius provides a gift, a way to study the structure of our own galaxy. Some studies suggest that its repeated plunges may have triggered star formation bursts within our galaxy. As it passed through, it may have stirred up clouds of gas, compressing them until they collapsed into new stars. If so, then the legacy of Sagittarius is not only in the stars it lost, but also in the stars it helped bring to life within the Milky Way. The relationship is parasitic and creative at the same time. Sagittarius is not the first dwarf galaxy to meet such a fate, and it will not be the last. The Milky Way's halo is littered with remnants of past meals, faint streams of stars that once belonged to other small galaxies or clusters. Each stream tells a story of a past encounter, but Sagittarius is unique because we are watching its destruction happen in real time. It is a rare case where the drama unfolds in the present, giving astronomers a front row seat to galactic cannibalism. What remains of Sagittarius today is a faint core orbiting about 70,000 light-years from the center of the Milky Way. It is still recognizable as a galaxy, but only barely. Compared to its likely original size, it is a shadow of itself. Its stars have been redistributed across the sky, some now indistinguishable from those born in the Milky Way. Over time, the core will continue to shrink until even that is gone, completely consumed by the larger galaxy it orbits. How many of the Milky Way's stars were stolen rather than born within it? How many ancient dwarfs were swallowed long before we had the tools to trace their remains? And how does this steady diet of smaller companions shape the growth and evolution of galaxies like our own? In Sagittarius, we see one answer unfolding, but the broader picture is that this is how galaxies grow. They consume their neighbors, merging and blending until their histories are inseparable. The Milky Way itself will one day merge with the Andromeda galaxy, an event on a far grander scale, but built on the same principles at work in Sagittarius's demise. The streams of stars from this small dwarf are the first hints of what happens when two galaxies cannot resist each other's pull. The Fornax dwarf, a galaxy rich with globular clusters. The Fornax dwarf spheroidal galaxy is a quiet and unassuming companion to the Milky Way, drifting some 460,000 light-years away in the southern constellation Fornax. At first glance, it looks like any other dwarf, faint, diffuse, and easily lost against the dark. Yet it carries a secret that makes it stand out among its peers. Fornax is home to not just one or two globular clusters, but at least 6 of them. For such a modest galaxy, this is extraordinary. The presence of so many globulars raises questions about how a system like Fornax came to be, and what its history can tell us about the balance between survival and destruction in the lives of dwarfs. Globular clusters are often thought of as hallmarks of large galaxies. The Milky Way hosts more than 150, each one a dense ball of hundreds of thousands of stars bound together for billions of years. These clusters tend to be old, with stars that formed near the dawn of the galaxy. Their very presence speaks of long histories and the ability to hold on to gas and material in the early universe. Fornax's 6 globular clusters are a surprise because dwarf spheroidals are generally thought to be fragile, lacking the gravity and mass to gather and keep such star cities. Yet here is a small galaxy, no more than a few billion solar masses at most, holding a collection of clusters that rivals even some mid-sized galaxies. The clusters themselves orbit at various distances around the Fornax dwarf, scattered like tiny jewels around a dim lantern. Some lie close to the galaxy's core, while others drift far enough that they seem on the edge of breaking free. Astronomers have studied them closely because their stars preserve fossil-like records of past conditions. Many of the clusters contain stars more than 10 billion years old, meaning they formed early in the history of the universe. Their survival inside Fornax suggests that the galaxy, though faint today, may once have been richer, holding more gas and experiencing bursts of star formation that gave rise to these ancient populations. Unlike the Sagittarius dwarf, which is being pulled apart in long streams, Fornax shows signs of being relatively stable. Its stars are not being stripped away in great numbers, and it has managed to hold on to its globular clusters. This hints that Fornax occupies a more favorable orbit, far enough from the Milky Way's gravitational claws to avoid immediate destruction. Located at nearly 500,000 light-years, it circles the Milky Way at a comfortable distance, where tides are weaker and the galaxy can preserve its structure. This isolation may be the reason why it has managed to keep its unique set of clusters for so long. But why does Fornax have so many globular clusters? That question continues to puzzle astronomers. One possibility is that Fornax was once more massive, with a deeper well of dark matter and more raw material. If the galaxy began its life larger and has since lost much of its outer material, the clusters we see today might be remnants from a more active past. Another idea is that Fornax captured some of its clusters during interactions with other small galaxies. In the crowded environment of the Milky Way's halo, galaxies occasionally brush past each other, exchanging stars or even swallowing smaller companions. Perhaps Fornax was in the right place at the right time to gather and keep more than its share. The clusters also tell us something important about the dark matter halo surrounding Fornax. To keep globular clusters in orbit for billions of years, a galaxy must have a stable and extended gravitational field. If Fornax were made only of its visible stars, the clusters would likely have drifted away long ago. Their continued presence is evidence of a larger, unseen structure anchoring them in place. Astronomers have also noticed that the globular clusters of Fornax may not perfectly match the galaxy's own star population. The clusters are typically older and more metal-poor, meaning their stars have fewer heavy elements compared to the more central stars of Fornax. This suggests that the galaxy had multiple episodes of star formation. First, an early rapid burst that produced the clusters, then a slower period where gas cooled and formed younger stars in its core. The clusters may be survivors of that first era, carrying the memory of Fornax's youth, while the main body of the galaxy reflects later stages of its life. Fornax's unique combination of stability and richness has made it a favorite target for telescopes. Both ground-based observatories and the space telescopes have mapped its stars, trying to piece together its story. Deep images reveal layers of stellar populations, from the oldest red giants to relatively younger stars formed only a few billion years ago. Unlike some dwarfs that seem frozen in time, Fornax appears to have continued forming stars well after its birth, though not at the furious pace of a larger spiral like the Milky Way. This extended activity may have played a role in its ability to host and maintain so many globular clusters. The contrast between Fornax and galaxies like Sagittarius shows how varied dwarf galaxies can be. Sagittarius, once larger, is being dismantled by the Milky Way's pull, leaving trails of stars across the sky. Fornax, more distant, has been left largely intact. Where Sagittarius is losing everything, Fornax has preserved treasures. Its clusters are like relics in a museum, hinting at an earlier, brighter time when the galaxy was more alive with star formation. Fornax is not as massive as the Magellanic clouds, yet it is not as fragile as the smallest ultra-faint dwarfs. Its star-forming history is richer than some, but quieter than others, and its abundance of globular clusters sets it apart entirely, challenging ideas about how such systems form and survive. The Sculptor and Sextans dwarfs. Sculptor and Sextans, both orbiting the Milky Way at moderate distances, are quiet companions. They illustrate a different side of galactic life, of slow evolution and long survival. The Sculptor Dwarf Galaxy lies about 290,000 light-years from Earth, orbiting on the outer edges of the Milky Way's gravitational pull. It was discovered in 1937 by Harlow Shapley, who noticed a clustering of faint stars in the constellation Sculptor. It is only visible through telescopes, and even then, it blends easily with the foreground of the Milky Way's own stars. To the human eye, it is a faint smear of light, but in reality, it is a spheroidal galaxy containing a few million stars. The galaxy hosts mostly old stars, with very little evidence of recent star formation. Unlike, say, the LMC, which is still actively producing new stars, Sculptor seems to have shut down that process billions of years ago. Its gas supply has either been stripped away or used up, leaving only the fossil record of its past in the form of ancient stars. These stars are metal poor. That scarcity of metals suggests Sculptor formed its stars early in the history of the universe, before multiple generations of supernovae could enrich the gas with heavier elements. Sextans, discovered later in 1990, is even fainter and more elusive than Sculptor. Located around 320,000 light-years from Earth in the direction of the constellation Sextans, it is among the lowest surface brightness galaxies known. To detect it, astronomers had to use careful counts of faint stars, since the galaxy itself is barely brighter than the background night sky. Sextans is a true ghost of a galaxy. Like Sculptor, it is a spheroidal dwarf, meaning it has a roundish, puffed-up appearance without the spiral arms or disks that larger galaxies often display. Its star population is small, numbering in the hundreds of thousands rather than millions. But the stars it does have tell a similar story. Most are old, with little evidence of ongoing star formation. Sextans, too, appears to have run out of gas long ago, leaving behind only the quiet glow of ancient suns. The calm nature of these galaxies might at first seem dull compared to the tidal streams of Sagittarius, or the brilliant activity of the Magellanic clouds. But because they are not being shredded apart or warped, they offer cleaner conditions for studying internal processes. Astronomers can look at their stars without worrying too much about recent disruptions and reconstruct a straightforward history of star formation. By comparing the metallicity of stars across different ages, researchers can trace how quickly Sculptor and Sextans enriched their gas with heavy elements before star formation shut down. The picture that emerges is one of galaxies that formed stars early, experienced a brief period of chemical growth, and then entered a long quiescence. This tells us that not every dwarf galaxy is destined for chaos. Some simply live quietly in the shadow of their host for billions of years. In cosmological simulations, small galaxies like Sculptor and Sextans are expected to be the most common building blocks of larger galaxies. These dwarfs merge together and with bigger systems, contributing their stars to galactic halos. Studying ones that still survive today helps confirm whether the simulations are right. The relatively simple nature of Sculptor and Sextans allows astronomers to compare them directly to predictions of how gas should cool, form stars, and eventually lose its fuel. If the models can reproduce galaxies like these, then scientists gain confidence in their larger framework for galaxy evolution. If not, then perhaps something about feedback from supernovae, gas loss, or dark matter needs to be reconsidered. In many cases, dwarf spheroidal galaxies appear to have far more dark matter than normal matter, making them excellent testbeds for the nature of this mysterious component of the universe. In fact, some of the strongest evidence for dark matter's presence in the universe comes not from grand spiral galaxies like the Milky Way, but from faint dwarfs like these. Sculptor has another distinction worth noting. Its stars are arranged in a pattern that suggests two overlapping populations. Some stars are more centrally concentrated and slightly richer in metals, while others are more spread out and metal poor. This hints at a complex history, perhaps involving more than one burst of star formation or interactions that stirred its contents. Even within a galaxy that seems quiet, subtle clues like this remind us that no galaxy is entirely uneventful. Sextans, with its extremely low density of stars, raises questions of its own. How did such a diffuse galaxy managed to form at all without being torn apart? And how has it avoided destruction by the Milky Way's tidal forces for so long? These puzzles keep astronomers returning to the faint smudges of light that at first glance might seem unremarkable. Seen in the larger portrait of the Milky Way's satellites, Sculptor and Sextans represent the understated side of the family. They do not boast sprawling bridges of gas, dramatic clusters, or obvious trails of destruction. Instead, they persist as dim but stable neighbors with their value lying in their simplicity. The Ursa Minor and Draco dwarfs, dark matter strongholds. If you were to look at the night sky without any aid, the Ursa Minor and Draco dwarf galaxies would never reveal themselves to you. They are invisible to the naked eye, only betrayed by the faintest sprinkling of stars when astronomers use deep imaging and sensitive instruments. Yet despite their quiet appearance, these two galaxies hide a vast amount of dark matter, outweighing their stars many times over. In fact, when it comes to the ratio of visible matter to invisible mass, few systems are as extreme as Ursa Minor and Draco. The Ursa Minor dwarf galaxy lies in the northern sky, close to the famous constellation of the Little Dipper. If you could travel there, you would find a faint collection of old stars, most of them having formed more than 10 billion years ago. It has very little gas left today, meaning that star formation shut down a long time ago. Draco, its neighbor, is much the same. Named after the constellation of the dragon that coils across the northern sky, the Draco dwarf galaxy is also a tiny, faint system dominated by ancient stars. Both of them are classified as dwarf spheroidal galaxies. They are not undergoing any dramatic events, and on the surface, they seem uneventful. But their true importance comes from what lies beneath. In Ursa Minor and Draco, dark matter dominates completely. Estimates suggest that more than 90% of their mass is made of dark matter. For every star that shines, there are countless invisible particles providing the real backbone of the galaxy. Their mass-to-light ratios are staggering, dozens, even hundreds of times greater than that of galaxies like the Milky Way. In other words, they are strongholds of dark matter. In the Milky Way, dark matter is mixed with stars, gas and dust in enormous quantities, making it hard to isolate. But in dwarfs like Draco and Ursa Minor, the picture is much cleaner. They are like magnifying glasses for dark matter physics. One of the big debates in cosmology is how dark matter behaves on small scales. The standard picture of cold dark matter predicts that galaxies should have dense, cuspy centers, where dark matter piles up toward the core. But observations of systems like Ursa Minor and Draco sometimes suggest flatter, cored profiles, where the density of dark matter is more spread out. This has sparked discussions about whether our models of dark matter need to be revised, or whether processes like supernova explosions reshape the matter in these tiny galaxies. Another related puzzle is the too big to fail problem. In simulations of the Milky Way surroundings, many dark matter halos appear that should be large enough to host bright dwarf galaxies. Yet when astronomers look around our galaxy, they don't find nearly as many luminous dwarfs as expected. Some halos seem to be completely dark, invisible, but still predicted to exist. This raises questions about the efficiency of star formation in small halos, and about whether dark matter behaves in ways the standard model doesn't capture. These galaxies live close to the Milky Way, well within its halo of dark matter. Over billions of years, the pull of the Milky Way could have disrupted them, just as it is tearing Sagittarius apart. Yet Draco and Ursa Minor remain relatively intact, though stretched and shaped by tidal forces. Their endurance hints that their dark matter halos are dense enough to shield them, acting like anchors that keep the galaxies from being fully shredded. In simulations of the universe, small dark matter halos are expected to form first and then merge to build larger galaxies like the Milky Way. Dwarf galaxies today are thought to be the survivors of that early age, the building blocks that never merged. By studying Draco and Ursa Minor, scientists get a glimpse of what those original structures might have looked like billions of years before the Milky Way became the giant spiral it is today. Both galaxies were first spotted in the 20th century through painstaking surveys of photographic plates. Today, with wide-field digital surveys, we can study them in far greater detail, mapping individual stars across their surfaces and even tracing their extended halos. Yet they remain elusive, requiring long exposures and sensitive instruments to reveal their true nature. Despite their quiet appearance, Draco and Ursa Minor are not irrelevant side notes. They are central to some of the biggest mysteries in modern astronomy. They might look like nothing more than faint smudges in the sky, but beneath their faint light lies a story about the unseen mass that shapes everything we know. The Booties and ultra-faint dwarfs, ghosts of the galactic halo. If the large and small Magellanic clouds are the bright, obvious companions of the Milky Way, then the Booties dwarfs and the so-called ultra-faint dwarfs are their exact opposite. They are barely visible, fragile things that often slip beneath the limits of what telescopes can find. When astronomers discovered them, many wondered whether these could even be called galaxies at all. They contain only a few thousand stars, sometimes only a few hundred, scattered across faint, ghostly structures. The Booties dwarf galaxy, first detected in 2006, gave astronomers their first real taste of what such ghostly companions looked like. Booties worst, the brightest of the group, is still incredibly dim compared to galaxies like Fornax. The stars inside Boots are some of the most chemically primitive that we've ever seen. After Boots came Boots 2, an even fainter neighbor. Boots II is so small and so dim that some astronomers questioned whether it should be considered a galaxy at all or just a stray star cluster. Its stars are spread widely, and the system shows signs of being tugged apart by the Milky Way's gravity. Yet even this fragile little structure carries secrets. By studying the motions of its stars, astronomers found that Boots II contains far more mass than its visible stars could account for, suggesting that it too sits inside a bubble of dark matter. If true, then Boots II is not simply a star cluster, but a galaxy in its own right, one whose stars are hanging on thanks only to the invisible gravity of dark matter. These discoveries opened the floodgates. With deeper sky surveys, astronomers began to uncover more and more of these faint companions scattered through the Milky Way's halo. They were given the name ultra-faint dwarfs, a fitting description of their almost ghost-like presence. Unlike the brighter dwarfs such as Fornax, the ultra-faints only appear in painstaking surveys of the sky, where astronomers carefully sift through billions of stars to find small clumps that share a common motion. Each new discovery added another faint, fragile point to the Milky Way's extended family. Many of their stars are thought to have formed more than 12 billion years ago in the first wave of star formation after the Big Bang. Unlike larger galaxies, which experienced multiple generations of star birth and chemical enrichment, the ultra-faints seem to have stopped forming stars very early. Their stars remain poor in heavy elements, frozen in a primitive state that reflects the universe's earliest chemistry. Some of the most famous ultra-faints, like Segway 1, exemplify this. Segway 1 is so dim that it emits less light than a single bright star. For years, astronomers debated whether it could really be a galaxy or just a chance grouping of stars. But its stars move in ways that suggest the presence of a hidden mass, once again pointing toward dark matter. What makes Segway 1 extraordinary is the metallicity of its stars. These stars are among the most metal-poor in the entire universe, marking them as survivors from the earliest epoch. In that sense, Segway 1 is not just a ghost of a galaxy, it is a fossil from the dawn of time. Another ultra-faint, Reticulum 2, stunned astronomers when its stars were found to be unusually rich in heavy elements created through rare neutron star mergers. This was unexpected because such tiny galaxies were thought to be too small to retain the products of such explosive events. Yet Reticulum 2 showed that even the smallest galaxies could bear witness to cataclysmic events, adding new layers to the story of chemical evolution in the universe. Each ultra-faint dwarf seems to tell a slightly different story, and together they sketch a mosaic of the early cosmos. Why do some dark matter halos host thriving galaxies, while others end up as barely visible ghosts? The leading idea is that the smallest halos formed stars early, but then the universe changed around them. When the first generations of stars lit up, they flooded the cosmos with radiation that heated and stripped gas from the smallest galaxies. Star formation ceased, leaving only a sparse handful of old stars behind. In this view, the ultra-faint dwarfs are the survivors of a cosmic purge, remnants of a time when only the largest halos could keep forming stars. They are also important because they test the predictions of cosmological models. Perhaps many more ultra-faints remain undiscovered, hiding in the faintest corners of the sky. Or perhaps not all dark matter halos are able to light up with stars. By searching for these ghostly galaxies, astronomers hope to bring theory and observation into closer agreement. Canis Major overdensity, a galaxy or just a ripple? If you look toward the constellation of Canis Major, the greater dog in the sky, you will be staring into one of the most debated regions in our galactic neighborhood. Here lies what astronomers call the Canis Major overdensity, a concentration of stars that has stirred up arguments since it was first noticed in the early 2000s. Unlike the Magellanic clouds or the Sagittarius dwarf, its status is not clear. Is it truly a small galaxy being consumed by the Milky Way? Or is it simply a ripple, a natural gathering of stars within our own galaxy's spiral disk? The Canis Major overdensity first came to attention through surveys that mapped the distribution of stars across the sky. Astronomers noticed that in the direction of Canis Major, there seemed to be an unusual clump of stars lying just beyond the Milky Way's thick disk. What made it especially interesting was that these stars appeared to follow their own path, hinting at the possibility that they belonged to a separate structure. If true, it would mean that the Milky Way was in the process of devouring yet another dwarf galaxy. The excitement grew because this overdensity appeared to be relatively close to us, only about 25,000 light-years from Earth, closer than most of the other known dwarfs. The idea of a dwarf galaxy so near to us was thrilling. Just like the Sagittarius dwarf, which leaves long streams of stars as it's pulled apart, the Canis Major system seemed to offer evidence of being shredded by the Milky Way's powerful gravity. Observers claimed to detect a structure called the Monoceros Ring, a vast arc of stars wrapping around the Milky Way's disk, which could be the remains of tidal streams linked to Canis Major. To many, this was a strong sign that they were seeing another captured galaxy dissolving into our own. But as with many discoveries, the story quickly became more complicated. Some astronomers pointed out that the Milky Way's disk is not a simple flat sheet. Instead, it bends and warps, with ripples and flares that can create patterns of stars that look like overdensities from our vantage point. In this view, the stars in Canis Major might not belong to a separate galaxy at all. They could simply be part of our own galaxy's outer disk, piled up in a way that makes them look distinct. What looked like the signature of an intruding dwarf might just be the Milky Way's natural structure, confusing the picture. The debate between these two views, galaxy or ripple, has never been fully settled. Different studies have offered conflicting results. Some surveys have shown populations of stars in Canis Major that appear older and more metal-poor, fitting the profile of a dwarf galaxy that formed separately. Others have found that the stars match the characteristics of Milky Way disk stars, suggesting that the overdensity is nothing more than a local bump in the galactic plane. The lack of a clear core or defined center makes the case weaker compared to systems like the Fornax or Sculptor dwarfs, which clearly have their own identity. One of the difficulties is that the Canis Major region sits in a crowded part of the sky. Looking through the disk of the Milky Way means looking through countless stars, gas, and dust. This heavy background makes it hard to sort out which stars belong to what structure. Unlike the Magellanic clouds, which stand out plainly against the dark backdrop of space, Canis Major blends into the Milky Way's glow. Untangling its identity requires careful measurements of star motions and chemical properties, and even then, the results are not always decisive. If Canis Major is a true galaxy, it would mean the Milky Way has consumed yet another companion, and we would be catching it in the middle of the act. Its stars, stretched out in the monocerous ring, would serve as a record of how galaxies grow by accretion. The Milky Way's halo, full of streams and faint remnants, would gain another confirmed example of stellar debris from a smaller victim. If, on the other hand, Canis Major is simply a ripple in the disk, the result is no less interesting. It would show that the Milky Way's own structure is more complex and dynamic than we once thought. Ripples and rings in the disk may be the scars of past encounters, perhaps caused by dwarf galaxies plunging through the plane and disturbing the stars. In this case, Canis Major might not be a galaxy itself, but the footprint left by one, an echo of an older collision that shook the Milky Way's outer regions. This would tie the overdensity to the broader history of galactic interactions, even if it lacks its own identity. Even in regions relatively close to Earth, only tens of thousands of light-years away, we are still discovering new structures and struggling to understand their nature. The fact that astronomers cannot agree whether this is a galaxy or not highlights how fuzzy the boundaries can be. Galaxies are not always clear, round islands of stars. They can blur into streams, rings, and overdensities, making it hard to draw a line between what counts as separate and what is part of the whole. Canis Major does not need to be firmly placed in one category to be valuable. Its study sheds light on the processes that shape the Milky Way, whether through the steady settling of stars in the disk or the violent shredding of smaller galaxies. It occupies a grey zone, showing that our cosmic neighborhood is messy and dynamic. Perhaps newer tools will soon settle the debate, showing once and for all whether Canis Major is a galaxy being consumed or simply a quirk of the Milky Way's disk. Until then, it remains an object of fascination, a reminder that the boundary between galaxies and their hosts is not always clear, and that sometimes the most interesting discoveries lie in the in-between. Gaia's galactic archaeology. The European Space Agency's Gaia mission was a spacecraft designed not just to map where stars are, but how they move. With Gaia, a new field has opened: galactic archaeology. It is the study of the Milky Way's history, not by digging into the ground, but by tracing the motions of stars, uncovering the hidden companions that long ago were swallowed by our galaxy. Gaia works by measuring parallax, the tiny shift in a star's position as Earth orbits the Sun. This allows astronomers to measure distances with exquisite precision, but Gaia does more than that. It tracks proper motions, the slow drift of stars across the sky, as well as their radial velocities, the speeds at which they are moving toward or away from us. When combined, these measurements give a three-dimensional map of how millions of stars are moving through the Milky Way. The sheer scale of the data has transformed how astronomers understand the galaxy's structure. Before Gaia, many of the Milky Way's faintest satellites and streams were essentially invisible. Their stars blended into the background. With Gaia, those same stars stand out, their shared motions betraying their common origin. One of the most dramatic discoveries to come from Gaia is the identification of the Gaia-Enceladus merger. This was not a dwarf galaxy drifting gently at the edge of the halo, but a massive system, perhaps 1/4 the size of the Milky Way itself, that collided with our galaxy billions of years ago. The evidence came not from star counts. There was no clear overdensity of stars that shouted, "Here is a galaxy," but from motions. Astronomers noticed that a large group of stars in the halo moved on highly eccentric orbits, plunging in and out through the Milky Way. Their chemical makeup was also distinct, poorer in metals than the native stars of the disk. Put together, it told a story of a great collision, one that shook the Milky Way and helped build the thick disk we see today. Without Gaia's ability to measure motion so precisely, these stars would have remained lost in the crowd. Counting stars can reveal nearby companions if they are dense enough, like the Fornax or Sculptor dwarfs. But most of the Milky Way's mergers left only scattered trails of stars. These trails are thin and faint, blending into the broader halo. Motions, however, do not blend so easily. A star that belonged to a captured galaxy keeps its orbital fingerprint long after the galaxy itself is gone. Gaia allows astronomers to read those fingerprints. By mapping not just where stars are, but how they are moving, it becomes possible to group them into families. Some families trace out streams. Others reveal entire past galaxies that merged and dissolved, leaving only their stars behind. Another key finding from Gaia is the Helmi streams, named after astronomer Amina Helmi, who first identified them. These are groups of stars moving together through the halo, bound not by gravity anymore, but by a shared history. Their orbits and compositions point to a single dwarf galaxy that was consumed 6 to 8 billion years ago. Again, the discovery was possible because Gaia provided velocity data that separated these stars from the surrounding field. In a normal star map, they were invisible. In Gaia's motion data, they stood out like arrows pointing in the same direction. Gaia has also uncovered substructures within the disk itself. Waves ripple it, bending it like a warped vinyl record. Some stars are kicked into vertical motions, bobbing above and below the galactic plane. These distortions may be the scars of past encounters, perhaps with the Sagittarius dwarf galaxy or other satellites that passed through. They suggest that even today, the Milky Way is still reshaping itself under the influence of its smaller companions. The disk is not a settled structure. It is a dynamic living system shaped by its history. Traditional methods of discovery relied on identifying clusters of stars in the sky, leading to the catalogue of known dwarfs orbiting the Milky Way. But Gaia has shown that some overdensities are not galaxies at all, but the shredded remains of once larger systems. Others that seem to be part of the halo are actually bound groups, faint dwarfs hiding in plain sight. Motion data provides the ability to disentangle these overlapping populations. It is like switching from a still photograph to a video, where the movement suddenly clarifies which stars belong together and which do not. Chemical analysis of stars tells astronomers about their birth environments. Stars formed in large galaxies tend to have higher metallicities than those born in smaller ones. Motion tells them about orbits. Combined, these data sets allow reconstruction of when mergers happened. For example, stars from Gaia Enceladus suggest a merger about 10 billion years ago. Other streams point to smaller events more recently. Piece by piece, Gaia is helping to build a chronology of the Milky Way's past, turning what was once speculation into something close to a family tree of mergers. The distribution of stellar motions also provides indirect evidence for the shape of the Milky Way's dark matter halo. If stars from a past merger move in ways that do not match visible matter, it suggests that unseen mass is shaping their orbits. By studying the motions of stars in streams and remnants, astronomers can probe the halo of dark matter surrounding our galaxy. The scope of Gaia's work is still expanding. Each new data release adds millions more stars, finer precision and greater depth. Already, astronomers have used Gaia to identify multiple possible past mergers, each with its own distinct stellar population. Some have evocative names: Sequoia, Tamnos, Arjuna. Each represents another galaxy lost to time. The faint dwarfs we see today, like Sculptor or Fornax, are just the survivors. Many others came before, leaving behind only streams, ripples, and odd motions. With Gaia, astronomers are no longer limited to the survivors. They can uncover the lost, the hidden, the galaxies long since consumed. It is galactic archaeology in the truest sense: cores, cusps, and the dwarf galaxy problem. In the study of galaxies, and especially of dwarf galaxies, one persistent puzzle has been the way dark matter seems to arrange itself. Theory and simulation tell us one story, but observations of the faintest galaxies often tell another. This gap between expectation and reality has become known as the Cusp-core problem. Dark matter seems to be spread out more smoothly than theory suggests, creating shallow central regions, or cores, rather than the steep spikes or cusps predicted by computer models. The origin of this problem lies in the earliest cosmological simulations run in the late 20th century. When researchers began to model the universe's growth under the influence of cold dark matter, they found that small clumps of this mysterious substance tended to form halos with sharp, concentrated centers. In these halos, density increased rapidly toward the middle, meaning that the closer one approached the center, the more extreme the gravitational environment became. These steep centers were given the term cusps, and they became a hallmark of cold dark matter theory. As computing power improved, more refined simulations were carried out, and again cuspy centers emerged as the default outcome. This suggested that cusps were not simply artifacts of the earliest models, but rather natural results of the way dark matter should behave under gravity. However, when astronomers turned to dwarf galaxies to test these predictions, the evidence was not so clear. The motions of stars within many dwarfs pointed to a much flatter distribution of dark matter near their centers. Instead of density spiking as one approached the middle, it leveled off, forming a core. The simplest way to picture this difference is to imagine a hill versus a plateau. A cusp is like a steep hill rising sharply from the ground, while a core is more like a flat plateau that remains level for a distance before dropping off. In terms of dark matter, a cusp means mass density becomes more and more extreme near the galaxy's center, while a core means the density stays relatively constant across a wider region. In larger galaxies like the Milky Way, stars, gas, and black holes complicate the measurement of central mass distributions. But in dwarfs, where visible material is sparse, the gravitational fingerprint of dark matter is clearer. The results, collected across numerous systems, point again and again to the presence of cores rather than cusps. Why is this a problem? Because if dark matter behaves as the simplest version of the theory suggests, cold, collisionless particles interacting only through gravity, then cusps should form naturally. Their absence means either the theory is incomplete or something has happened inside these galaxies to erase the cusps and create cores. Researchers have approached this puzzle from both angles. On the astrophysical side, one explanation involves the role of stars and supernovae. Though dwarfs are faint and contain relatively few stars, they can still experience bursts of star formation that briefly transform their internal structure. When massive stars die in violent explosions, they pump energy into the surrounding gas, pushing it outward. This process, repeated many times over the lifetime of a dwarf galaxy, can stir the gravitational potential well, causing dark matter to redistribute. In essence, repeated supernova-driven heating may puff up the inner dark matter, flattening cusps into cores. This idea has gained traction in recent years, as simulations that include not only dark matter, but also baryonic physics, stars, gas, and feedback, sometimes produce core-like distributions more in line with observations. It suggests that what appears to be a failure of dark matter theory might instead be an incomplete picture of how galaxies evolve. Without accounting for the messy processes of star formation, simple dark matter-only simulations may misrepresent what actually occurs inside dwarfs. Yet, not everyone is convinced this solves the problem. Some dwarfs show signs of having very little recent star formation, yet still appear to contain cores. Others suggest that the degree of feedback required to erase cusps might be too extreme, given the small number of stars present. In such cases, astrophysical explanations may not be enough, forcing researchers to consider whether dark matter itself behaves differently than the cold, collisionless picture. This leads to more exotic possibilities. One proposal is that dark matter might be self-interacting, meaning that dark matter particles occasionally collide with one another. Unlike normal matter, which collides and radiates energy easily, dark matter is thought to be nearly invisible in its interactions. But if it does interact slightly, then over long timescales, those collisions could naturally redistribute particles inside galaxies, smoothing out cusps into cores. Self-interacting dark matter has become one of the leading alternatives to the cold dark matter model, precisely because it can help solve the Cusp-core issue. Other theories suggest that dark matter may not be made of heavy, cold particles, and instead it could consist of lighter, wave-like particles that naturally spread out, resisting the formation of sharp cusps. Ideas like fuzzy dark matter, where ultralight particles create quantum pressure that softens central densities, provide another potential path to explaining cores. These alternative dark matter models are attractive because they can explain dwarf galaxy observations without requiring as much reliance on complex baryonic feedback. However, they come with their own challenges. For example, if dark matter were too fuzzy or too strongly self-interacting, it could alter the structure of galaxies on larger scales, contradicting other well-tested aspects of cosmology. Researchers must therefore balance these ideas carefully, seeking models that fit dwarf galaxies without breaking the successes of dark matter theory elsewhere. Observationally, the Cusp-core debate continues to be tested with better data. Instruments that can track the motions of individual stars in faint dwarfs are critical, as they allow astronomers to map mass distributions more precisely. Surveys have provided the stellar velocities needed to construct detailed models of galactic structure. In parallel, radio telescopes that measure the motion of gas in some dwarfs offer complementary insights. The problem remains stubborn because not all dwarfs tell the same story. Some appear to have clear cores, while others seem more compatible with cusps. This variety raises the possibility that both outcomes may occur, depending on the specific history of each galaxy. A dwarf that experienced violent bursts of star formation might develop a core, while one that evolved more quietly could retain a cusp. In this view, the cusp-core problem is less about a universal mismatch and more about a spectrum of possibilities shaped by local conditions. The role of dwarfs in building the Milky Way's halo. Unlike the bright spiral arms or the dense central bulge of the Milky Way, the halo is diffuse and faint, stretching far beyond the visible disk. It is a sphere of scattered stars, globular clusters, and traces of past activity. The halo looks almost empty at first glance, but it carries with it the history of the Milky Way's formation. Most scientists today believe that the outer halo was not built from inside the galaxy, but rather from the remains of many smaller galaxies. The idea that the halo is a graveyard of galaxies goes back to the late 20th century. Even then, researchers noticed that stars in the halo were different from stars in the disk. Halo stars tend to be old, with low metallicities. The disk is full of younger, more metal-rich stars, constantly refreshed by cycles of starbirth and supernova explosions. But the halo appeared frozen in time. Dwarf galaxies offered a natural explanation. These small systems have limited star formation. They often run out of gas early and never build up large amounts of heavy elements. If a galaxy like the Milky Way tore them apart and scattered their stars into space, the remnants would look very much like what we now observe in the halo. As sky surveys expanded, astronomers began to spot real evidence of past mergers. Streams of stars, tidal tails, and clumps of unusual stellar populations all pointed toward dwarf galaxies being digested by the Milky Way. Over time, these features spread out and blurred, eventually blending into the background of the halo. The process is so slow that even after billions of years, the marks are not fully erased. By carefully mapping the sky and measuring star motions, researchers can still pick out where one galaxy once ended and another began. The halo, then, can be thought of as a quilt stitched together from many smaller galaxies. Each dwarf that fell into the Milky Way left behind not only its stars, but also its dark matter, globular clusters, and chemical fingerprints. When astronomers look at halo stars with spectrographs, they sometimes find unusual element ratios that don't match typical Milky Way stars. These chemical oddities act like passports, proving that the star came from another system. By gathering enough of these signatures, scientists can reconstruct the history of how many dwarfs were absorbed and when. It is now widely accepted that the Milky Way's halo was built in two phases. The inner halo, closer to the galactic center, seems to contain stars that may have been formed inside the Milky Way itself or came from one or two particularly massive mergers. The outer halo, stretching hundreds of thousands of light-years into space, appears much more chaotic, with stars arriving from a variety of smaller dwarfs. The distinction between inner and outer halo has become clearer with data from the Gaia mission. One of the most famous examples is the Gaia-Enceladus merger, sometimes called the Gaia sausage because of the shape it produced in velocity space. Another massive contributor was the Sagittarius dwarf, but these are not unique. Dozens of smaller dwarfs have likely disappeared entirely, leaving only their stars scattered across the halo. Many of these mergers happened so long ago that the streams have fully dissolved. When we look at the outer halo today, the distribution of stars is patchy and irregular. Computer simulations confirm this picture. Large galaxies grow by accreting smaller ones, and their halos serve as the long-lasting record of that growth. Many globular clusters orbiting in the outer halo have chemical properties that suggest they did not form inside the Milky Way. Instead, they likely originated in dwarfs that were later destroyed. These clusters survived the fall, remaining intact while their parents were shredded. By studying which clusters share chemical or orbital features, astronomers can group them into families. The dark matter halos of dwarfs are harder to trace directly, but simulations predict that dark matter from cannibalized dwarfs is now mixed into the Milky Way's own dark matter halo. If true, then even the invisible skeleton of the galaxy was shaped by the slow reign of dwarfs over billions of years. The Milky Way is still accreting new material, still tugging at nearby dwarfs. Future astronomers will see their stars join the halo, their unique fingerprints recorded in the chemical and kinematic fabric of the galaxy. Large galaxies are mosaics, built from countless smaller units. The Milky Way's halo is the clearest reminder, a diffuse archive of stars that once belonged to dozens of independent galaxies. The chemical fingerprints of dwarf galaxies. Stars in dwarf galaxies often show element ratios that are unusual compared to stars in the Milky Way. One of the most striking patterns concerns the balance between what astronomers call alpha elements, like magnesium, calcium, and silicon and iron. In the Milky Way, older stars show high ratios of these alpha elements to iron, reflecting enrichment by massive stars that exploded as supernovae early in galactic history. As time went on, smaller stars also contributed iron through a different kind of explosion, type Ia supernovae, and the balance shifted. In dwarf galaxies, however, this shift often appears at much lower overall metallicity than in the Milky Way. This suggests that dwarf galaxies had slower, less efficient star formation, so the influence of type Ia supernovae became important earlier in their chemical history. This means that the stars in dwarf galaxies preserve a record of a very different pace of evolution. By comparing the chemical fingerprints, astronomers can tell which Milky Way stars might have originated in a smaller system that was later absorbed. Another clue comes from elements heavier than iron, which are formed in rare processes involving neutron capture. There are two main channels: the slow process, or S process, where elements build up inside aging giant stars, and the rapid process, or R process, which happens in extreme events like neutron star mergers or certain kinds of supernovae. Dwarf galaxies often show unusual patterns in these heavy elements. Some are deficient in them, reflecting the fact that few such rare events ever occurred in their small populations. Others, however, show sudden bursts of R-process enrichment, likely from a single dramatic event that seeded the entire galaxy with heavy elements. The ultra-faint dwarf reticulum 2, for example, contains stars with enormous amounts of R-process elements, suggesting that a single neutron star merger early in its history was enough to leave a chemical signature across the entire system. This kind of finding tells us that even in the smallest, faintest galaxies, the fingerprints of individual cosmic events can dominate the chemical record. Where in the Milky Way, such signals are washed out by billions of stars mixing over billions of years. In dwarfs, they remain crisp and clear. This makes dwarfs precious for testing theories of nucleosynthesis, the creation of elements inside stars and stellar explosions. There are also stars in dwarfs that seem to be among the most primitive known anywhere. Studying their chemical fingerprints allows astronomers to peer back toward the earliest cosmic times, when the very first supernova seeded the universe with elements beyond hydrogen and helium. Such stars carry direct evidence of processes that occurred more than 13 billion years ago. A fascinating detail is how chemical enrichment ties into star formation efficiency. In the Milky Way, the sheer mass of the galaxy helps trap gas, recycle it, and create stars continuously. In dwarfs, by contrast, even a modest burst of star formation can blow out much of the galaxy's gas, halting star formation for hundreds of millions of years. During that time, no new stars form to lock away chemical signals. When the gas eventually cools and stars start forming again, the chemical fingerprint has shifted because of enrichment from past supernovae. This stop-and-go process produces unique patterns in the ratios of elements. Another angle concerns the use of chemical tagging. This is the idea that groups of stars born from the same cloud share the same chemical fingerprint. In large galaxies, this can be very hard to apply because so many stars overlap in chemical space. But in dwarf galaxies, the small populations make it easier to identify families of stars with common origins. This has led to insights about how these galaxies grew, whether they experienced one major burst of star formation or several smaller ones, and how external factors like interactions with the Milky Way may have altered their histories. The ongoing work of spectroscopic projects like Apogee and DESI is making this picture sharper. By gathering chemical fingerprints for millions of stars, astronomers are not only cataloging what exists today, but also tracing the family tree of galaxies. Dwarf galaxies, with their unusual and sometimes extreme element ratios, are proving to be the key to unlocking how galaxies formed, how elements were forged, and how the universe itself built up the diversity of matter we see today. The satellites we haven't found yet. The Milky Way is almost certainly surrounded by a swarm of invisible companions waiting to be uncovered. Identifying them is a task that requires not just better telescopes, but also clever analysis. It involves sifting through data, separating real patterns from random noise, and recognizing when a loose clump of faint stars is actually a galaxy in its own right. What makes this hunt exciting is that every new dwarf found reshapes our understanding of how the Milky Way came to be. Each discovery helps test theories of galaxy formation, star formation, and dark matter. If the predictions are correct, then the majority of our galaxy's satellites remain hidden. Newer generation of surveys, especially those covering wide patches of the sky in exquisite detail, will be crucial. Astronomers are especially eager for the Vera C. Rubin Observatory, which is just about to begin full operations in late 2025. Its wide and repeated scans of the sky should pick out faint dwarfs that were previously overlooked, filling in the map of our galactic neighborhood with more companions. Some dwarfs may also be hidden because they are located in tricky places. If a small galaxy lies behind the bright band of the Milky Way's disk, its light can be drowned out by the sheer density of stars and clouds in our line of sight. The glare of starlight and dust makes it extremely difficult to separate a satellite from the background. This means that many of the missing dwarfs might actually be lurking right in the direction we tend to avoid in sky surveys. Finding them requires new ways of peering through dust and starlight, such as using infrared light, which can cut through cosmic haze more effectively than visible light. There's also the possibility that some of the unseen dwarfs are not just faint, but almost entirely dark. In other words, they may be galaxies where dark matter dominates almost completely, with hardly any stars lighting them up. If such objects exist, they would be nearly impossible to find directly. They would only reveal themselves through their gravitational effects, perhaps by the way they tug on streams of stars in the Milky Way's halo or distort the motion of gas in the outskirts of our galaxy. Already, astronomers have been surprised by the dwarfs discovered in the last 2 decades. Some are astonishingly faint, like Segway 1, which has fewer stars than a typical star cluster, but a mass dominated by dark matter. Others, like Crater 2, are enormous in size but diffuse, spreading their stars over a wide area with barely any central brightness. These finds suggest that instead of neat, compact dwarfs, the unseen satellites might come in a variety of shapes and structures, forcing scientists to expand their definitions. Beyond the Milky Way, the search extends to our nearest big neighbor, the Andromeda galaxy. Andromeda already has a rich system of satellites, some of which are surprisingly aligned in thin planes, raising questions about how they formed. Yet here too, many satellites are predicted but not yet observed. The same applies to other nearby galaxies, such as the Triangulum galaxy. If the missing satellites problem exists everywhere, then it's not just about our Milky Way, but a deeper issue tied to the way small galaxies form across the universe. A century ago, astronomers didn't even know about dwarf galaxies. It wasn't until surveys deepened and methods improved that these small companions began to show up. Each generation of tools reveals more faint and elusive systems, suggesting that our picture is always incomplete. The satellites we haven't found yet may simply be waiting for the next leap in observation. In that sense, the story of the missing dwarfs is as much about the limits of our instruments as it is about the galaxies themselves. If more ultra-faint dwarfs are found, it would bring the observed numbers closer to predictions, helping to bridge the missing satellites problem. If, on the other hand, the new discoveries continue to fall short of expectations, it would point to something deeper being wrong in our models. Either outcome would be significant. Some of the unseen dwarfs may already be gone, having been completely destroyed by the Milky Way. Their stars might now be scattered in streams across the halo, their dark matter halos merged into the larger structure of our galaxy. If this is the case, then the missing companions are not truly missing. They are ghosts, their remnants spread out across the sky. Stripped to the bone, how satellites lose their gas. Gas is the raw fuel for star formation, and without it, a galaxy becomes quiet, fading into a system where stars only age and die with little chance of new ones being born. Many of the dwarf galaxies that sit close to our own galaxy are almost entirely devoid of gas. They look barren compared to what we think of as a normal galaxy. This strange emptiness has a story behind it, one that involves not just gravity, but also the physics of how gas behaves in space and the violent forces at play when galaxies interact. One of the main ways a dwarf galaxy loses its gas is through a process known as ram pressure stripping. To imagine this, picture a car moving quickly down a highway with the windows open. The air pushes hard against anything loose inside, trying to blow it out of the car. Now replace the car with a small galaxy and the rushing air with the hot, thin plasma that fills the space between galaxies, called the intracluster or circum-galactic medium. As the dwarf galaxy speeds through this medium, the gas inside it feels the push, and if the pressure is strong enough, the gas is blown out into space. This can happen dramatically when a satellite plunges through the halo of gas surrounding a massive galaxy like the Milky Way. The stars, which are much heavier and less affected by this kind of drag, remain behind. But the gas, the lifeblood of the galaxy, is stripped away. This explains why many dwarf spheroidal galaxies, which are common satellites in our local group, are so gas-poor. They orbit close to the Milky Way and have been exposed to strong stripping effects for billions of years. Some of them may once have looked more like the LMC, but after multiple passes through the Milky Way's halo, they were stripped down to their bare bones. Today, they shine faintly with ancient stars, while their gas, once dense and bright, has long since been blown into the Milky Way's environment. But ram pressure is only one piece of the story. Another major process is tidal stripping, which is caused by gravity itself. When a smaller galaxy orbits a larger one, the difference in gravitational pull creates powerful stresses. These stresses can tear away stars. Gas is even more vulnerable to this process because it can be pulled away more easily. In some cases, the stars in the center remain intact while both gas and outer stars are peeled away. What is left behind is often a smaller, fainter version of the galaxy, orbiting like a remnant of its former self. There is also the role of the galaxy's own stars. Star formation itself is a violent process. When a new generation of massive stars forms, many of them quickly explode, releasing tremendous amounts of energy. In a large galaxy, the gravity is strong enough to keep most of this material bound. But in a dwarf galaxy, the gravitational pull is weaker. The shock waves and winds from supernovae can push gas outward, and once it is far enough from the center, other processes like ram pressure or tidal stripping can finish the job, carrying it away permanently. This self-driven loss makes it even harder for dwarfs to hold on to their material. One dramatic example of stripping is seen in jellyfish galaxies, which are not dwarfs but larger galaxies that show long trailing tentacles of gas streaming away as they move through clusters. The same physics applies to dwarfs, only on a smaller scale. If a dwarf plunges too close to the hot gas halo of a massive galaxy or cluster, it can leave behind long, thin trails of stripped gas, sometimes glowing faintly as stars form inside them. These trails are the last sign of the galaxy's lost potential, showing where its star-forming material was stolen away. In the local group, astronomers can directly see the differences between dwarfs that have been stripped and those that have not. Satellites like Sculptor, Draco, or Ursa Minor orbit closer to the Milky Way and have been stripped again and again until little more than their stellar skeletons remain. Gas-rich dwarfs arriving from the outskirts are slowly transformed into barren systems as they are drawn deeper into the halo. Interestingly, Andromeda's halo of hot gas may even be more extended and more massive than that of the Milky Way, making its stripping effect stronger. Observations of faint stellar streams around Andromeda also show that stripping is not just about gas, it is actively dismantling the galaxies themselves, scattering their stars into Andromeda's outer halo. Over time, these processes combine to produce a kind of natural selection. The dwarfs that fall into a giant galaxy's orbit are gradually robbed of their ability to make new stars. Some may survive as faint satellites, their structure preserved but their future cut off. Others may be shredded entirely, their stars forming streams that blend into the halo of the larger galaxy. In every case, the stripping reshapes both the small galaxy and the giant it orbits. The stripped gas can fall onto the host, fueling new star formation, while the stripped stars help build its halo. The fate of a dwarf galaxy, then, depends on where it orbits, how fast it moves, and how much gas it started with. A dwarf that remains far from the host may keep its gas for billions of years, continuing to form stars. A dwarf that plunges deep inside the halo may lose everything in just a few close passes. Some may even be reduced to ultra-faint galaxies. These faint remnants show us the end state of the stripping process. The satellites beyond satellites, sub-sub-galaxies. If the Milky Way has satellites, could those satellites themselves have satellites? Could the cosmic hierarchy extend one more step down, forming what might be called sub-sub-galaxies? Is there a natural limit to how far down the ladder one can go? When astronomers run large simulations of the universe, they feed in the basic ingredients: dark matter, gas, radiation, and the physics that governs their behavior. Out of those simulations comes the cosmic web, with filaments and nodes where galaxies form. Zooming in closer, one finds halos of dark matter that should host galaxies, and within those halos, smaller halos that should host smaller galaxies. Theoretically, there is nothing to stop the process from continuing further, with halos inside halos inside halos, much like Russian nesting dolls. If this picture is correct, then a dwarf galaxy, say one like Fornax or Sculptor, should itself have tiny companions clinging to it, faint little galaxies that orbit their larger but still modest parent. The difficulty is that such systems would be extremely hard to find. The Milky Way's own dwarfs are already faint and elusive, discovered only with careful surveys and deep imaging. A sub-satellite galaxy would likely be even dimmer, its stars so few that only the nearest examples might ever be visible. The dark matter halos predicted to host them could exist without producing much starlight at all, making them effectively invisible. Still, if even one such system could be found, it would be a strong confirmation that the hierarchical picture of structure formation is right down to the smallest scales. Hints that such systems might exist come from looking closely at the more massive dwarfs. Take the LMC and SMC. They are relatively large as dwarfs go, and both show signs of having interacted with smaller companions. A few tiny, faint objects discovered in their vicinity could in fact be satellites of the clouds, rather than of the Milky Way itself. If confirmed, that would mean we already have evidence for sub-sub-galaxies right on our cosmic doorstep. It also raises the intriguing possibility that some of the stars and gas being stripped away from the Magellanic clouds into long tidal streams might have originated from smaller companions caught in their gravitational pull. But what about smaller dwarfs? Could a faint spheroidal galaxy like Draco, itself barely clinging to survival in the Milky Way's tidal field, truly have its own even tinier companions? Here the answer is less clear. Theoretically, dark matter models suggest that every halo, no matter how small, should have substructure. But the shallower the potential well of the main dwarf, the less likely it is to hold on to such companions in the face of the Milky Way's overwhelming gravity. Any sub-sub-galaxy would need to be extremely close to its parent to avoid being torn away. It would orbit more like a satellite moon than a far-flung companion, huddled tightly to the core. Their faint starlight would blur into the background of their parent stars, making them nearly indistinguishable. Ultra-faint companions of ultra-faints would be systems with only a few hundred stars, bound together more by their shared dark matter halo than by gravity between the stars. To detect them, one would likely need not just imaging, but also measurements of stellar motions, looking for groups of stars that move together as if they belong to a hidden structure. In principle, similar data to Gaia could one day reveal whether dwarfs like Fornax have tiny clumps of stars moving in ways that betray a deeper connection. If sub-sub-galaxies exist, do they form stars the same way as larger galaxies? Or are they so faint and fragile that their gas gets stripped away almost instantly? Perhaps many of them are dark, miniature halos with little or no star formation, invisible to us except through gravitational effects. In that case, they might still be detected indirectly by their influence on the dynamics of stars in their parent dwarf or by the way they create subtle distortions in tidal streams. Centuries ago, scientists wondered whether the solar system could have its own smaller systems within systems. Planets with moons, moons with even smaller moons. In time, we discovered that yes, some moons do have companions, though usually they are small captured objects rather than stable long-term systems. The same question now arises on the galactic level. How far down does the nesting go? Does the cosmic hierarchy stop at dwarfs, or does it keep going one more step? If sub-sub-galaxies are confirmed, they would change how we think about the Milky Way's extended family tree. No longer would it be a simple story of large galaxies surrounded by small ones. Instead, the picture would become more complex, with a branching structure where even modest dwarfs carry their own miniature entourages. This would make galactic archaeology richer but also harder, because one would need to untangle not just the history of the Milky Way consuming dwarfs, but also dwarfs consuming their own satellites before being consumed themselves. The chemical signatures of stars, the patterns of stellar streams, the shapes of tidal debris, all would need to be reinterpreted with this added layer of complexity. Speculative though it is, the notion of sub-sub-galaxies fits naturally into the broader theme of the universe as a structure built from hierarchies. Galaxies form within dark matter halos, which themselves sit within larger halos, and so on. On scales both vast and minute, gravity seems to favor the building of nested systems. Whether there is a limit, whether the ladder of satellites stops here or goes one step further, remains a question that could, in principle, be answered in the next few decades as our ability to trace faint structures and subtle motions extends. Comparing the Milky Way and Andromeda's satellite systems. In our local group, the Milky Way and Andromeda seem like twin giants ruling their own territories. Both are spiral galaxies, both surrounded by swarms of dwarf companions, and both slowly moving toward a cosmic collision billions of years in the future. Yet when scientists begin to compare their satellite systems in detail, the picture becomes less balanced. Andromeda seems to have more satellites, different kinds of satellites, and in some ways, a richer set of examples that challenge what we think a galaxy family should look like. This head-to-head comparison of the two systems is great for testing ideas about galaxy formation, cosmic environment, and the role of dark matter in shaping small-scale structures. One of the clearest differences lies simply in the numbers. The Milky Way has, at last reliable counts, about 60 known dwarf satellites, though new discoveries continue to add to that list. Many of these are ultra-faint galaxies, hard to see even with modern surveys. Andromeda, however, boasts a larger population, with at least 90 confirmed satellites, possibly more depending on how deep observations go. Some of this difference comes down to vantage point. We live inside the Milky Way, so faint dwarfs near our disk are often hidden behind dense fields of obstructions. Observing Andromeda, by contrast, means looking at its system from the outside, which makes its satellites easier to map. Still, even after accounting for biases, Andromeda seems to have genuinely more companions. Did Andromeda simply form in a way that favored capturing or retaining more dwarves? Or has the Milky Way lost some of its former satellites over time through tidal stripping and past mergers? Beyond the raw numbers, the mix of satellite types also differs. The Milky Way's satellite system is dominated by ultra-faint dwarfs and a handful of brighter examples. Most Milky Way satellites, like Draco or Ursa Minor, are gas-poor spheroidals with little or no current star formation. Andromeda, however, has several bright satellites of its own, including M32 and M110, both of which have histories that seem more violent. M32, for instance, may be the stripped-down remnant of a once larger galaxy, its outer layers torn away by Andromeda's gravity. M110 shows evidence of past star formation episodes that suggest bursts triggered by tidal interactions. Even the smaller Andromeda dwarfs show different chemical fingerprints compared to Milky Way companions, hinting at different paths of enrichment and star formation over time. Several studies have suggested that a large fraction of Andromeda's satellites lie in a giant, thin plane, almost like a cosmic disk of dwarfs orbiting together. This is not what theory predicts. Dark matter simulations tend to produce satellites distributed in more spherical halos, not neatly arranged planes. Some scientists argue the pattern may be partly coincidental, but the alignment is too strong to dismiss entirely. By contrast, the Milky Way satellites are somewhat more scattered, though even here, hints of planar alignments have been suggested. If Andromeda's plane is real, it may mean that groups of satellites fell in together as coherent associations, rather than arriving one by one. Many of the Milky Way's dwarfs appear to have shut down their star formation long ago, turning into fossil systems. In Andromeda, some of its satellites show evidence of more extended histories, with star formation lasting longer or restarting after initial pauses. This suggests that Andromeda may have influenced its companions differently, perhaps because its gravitational tides or past mergers created more complex interactions. Understanding why Andromeda's dwarfs are more chemically diverse and historically active could help explain why two seemingly similar host galaxies ended up with such different families. There is also the matter of satellite brightness and detectability. The Milky Way's ultra-faint dwarfs are so dim that some contain only a few thousand stars. Andromeda surely has equivalents, but at its greater distance, about 2.5 million light-years, they are extremely hard to spot. Current surveys are just barely reaching the limit where such systems could be identified. Improved instruments may eventually bring its faint end into closer alignment with the Milky Way's. But if it doesn't, and if Andromeda truly lacks the same abundance of ultra-faints, then the difference may point to deeper physical causes, such as variations in how dark matter subhalos light up with stars in different environments. The Milky Way's Magellanic clouds are unique because they are massive enough to have their own satellite candidates. Their ongoing interaction with the Milky Way is creating the Magellanic stream. Andromeda does not seem to have direct equivalents of this kind of paired, gas-rich companions, though some argue that M32's history as a stripped galaxy represents a parallel case of a massive neighbor reshaped by tidal forces. The fact that the Milky Way has its own special configuration with two bright irregulars that are still very much alive and forming stars highlights how each host galaxy builds a unique environment for its satellites. From a theoretical perspective, the Milky Way-Andromeda comparison is invaluable. By examining two spiral giants of similar mass and age, but with different satellite systems, astronomers can test whether discrepancies are due to observation, environment, or physics itself. If satellite alignments like Andromeda's turn out to be common, then our cosmological models will need to adapt. If the Milky Way's satellites are unusually quenched and faint, then that may point to something peculiar about our galaxy's halo environment. Each difference becomes a test case, a way of probing the limits of our models. In many ways, the Milky Way and Andromeda resemble siblings, similar backgrounds but distinct personalities. Their differences remind us that even two neighbors in the same cosmic group can take separate paths, shaped by the accidents of mergers, tides, and local environment. By continuing to compare them, astronomers hope not only to understand each system more clearly, but also to uncover the general rules that govern galaxy formation throughout the universe. The local group is a testbed. The local group is neither a crowded cluster, where galaxies crash together too often to trace their slow histories, nor is it too empty, where interactions might be too rare to notice. Instead, it is a loose assembly of three large galaxies, the Milky Way, Andromeda, and the smaller but still significant Triangulum, surrounded by more than 80 dwarf galaxies of varying shapes, sizes, and brightness. This mix of giants and minnows creates a miniature version of the broader universe, scaled down to a distance range we can actually resolve with telescopes. For astronomers, the local group is something like a test field. By comparing how dwarfs orbit the Milky Way with those around Andromeda, and then looking at how Triangulum interacts with both, they can build a richer picture of the forces that govern galaxy formation. The individual dwarfs represent snapshots of different evolutionary stages. Each system carries its own imprint of past mergers, chemical histories, and environmental effects. The local group makes these comparisons possible in a way that studying distant clusters cannot. Triangulum is often overshadowed by its larger neighbors, but it plays an important role in this laboratory setting. As the third major spiral galaxy in the local group, it is smaller and less massive than the Milky Way or Andromeda, but large enough to host its own system of dwarfs. These companions are harder to study because Triangulum is farther away, but they provide a critical third point of comparison. If Andromeda's satellites look different from the Milky Way's, Triangulum helps decide whether that difference is unique to Andromeda or part of a broader pattern. For example, if both Andromeda and Triangulum show more satellites with elongated structures, while the Milky Way's are more compact, that suggests something about environment and history rather than chance. The local group also offers a chance to study how dwarfs interact not only with their giant hosts, but also with each other. In some cases, small galaxies orbiting near each other may form temporary pairs, their mutual gravity tugging at their stars even before the larger galaxy's pull takes over. There is evidence that some of the Milky Way's companions once entered together as small groups, already linked by gravity, before falling into our galaxy's halo. The same may be true for Andromeda. These associations of dwarfs are like smaller versions of the local group, showing how cosmic structure builds up from the bottom. By mapping out their positions and motions, astronomers can begin to reconstruct which dwarfs came in as individuals and which arrived as part of larger infalls. Some local group dwarfs show extremely primitive chemistry, others reveal a richer history. By comparing these patterns across dwarfs tied to the Milky Way, Andromeda and Triangulum, astronomers can test whether the giants shaped their satellites' chemical lives, or whether the dwarfs largely set their own pace before being captured. Dark matter studies, too, benefit from the local group's arrangement. Because we can measure the motions of stars in nearby dwarfs with great precision, the local group's dwarfs provide strong tests of how dark matter is distributed on small scales. And by having three main host galaxies, each with their own satellite system, researchers can ask whether the cores versus cusps problem shows up everywhere or only in specific environments. The Milky Way and Andromeda are on course to collide, and Triangulum may be drawn into that drama as well. Their dwarfs will be caught up in the process, stripped, merged, or scattered. Some of the faintest satellites could dissolve entirely, their stars adding to the smooth halos of the giants. Others may survive, but be flung into new orbits. The local group offers not only a snapshot of current conditions, but a preview of future galaxy evolution on a small scale. Studying it now allows astronomers to anticipate the fates of larger systems elsewhere in the universe. For many dwarfs within the local group, astronomers can resolve individual stars rather than just blended light. That means they can measure distances more accurately, identify variable stars that serve as cosmic yardsticks, and even trace star formation histories by counting stars of different ages. This level of precision is impossible for dwarfs in more distant groups where they appear only as faint smudges. The local group thus provides a kind of ground truth against which models and theories can be tested before being applied to galaxies farther away. The local group is small by cosmic standards, but in its modest boundaries it contains a universe of lessons. By looking at it as a whole rather than only at the Milky Way, astronomers can see the interplay of 3 major galaxies and dozens of dwarfs, each adding a piece to the puzzle. The fate of the Magellanic clouds in the Andromeda collision. Looking into the future of the Milky Way, one event dominates all predictions: the inevitable collision with the Andromeda galaxy. This enormous encounter will slowly reshape the sky, mixing stars and blending gas clouds. But while the drama of 2 giant spiral galaxies merging tends to capture the imagination, there are quieter but equally intriguing questions that arise when we think about the smaller players in this cosmic dance. Chief among them are the LMC and the SMC. What will become of them when their parent galaxy collides with Andromeda? As discussed earlier, the LMC may be massive enough to tug at the Milky Way's dark matter halo, and even shift the balance of our galaxy's motion. This means that when Andromeda enters the stage, the Magellanic clouds will not just be passive observers swept up by whatever happens. They will be dynamic participants, each bringing their own gravitational influence, gas clouds and orbits into the larger collision. Their future is tied not just to the Milky Way, but also to the timing of when the galaxies meet. Simulations of the Milky Way-Andromeda collision suggest that the first close approach between the 2 giants will happen about 4 billion years from now, with a complete merger following a few billion years later. By that time, the LMC and SMC may no longer look like the lively, irregular galaxies we know today. Tidal forces are already slowly pulling them apart, and the Milky Way's gravitational field is stripping their gas. Some models predict that within a few billion years, the Magellanic stream will have emptied most of their fuel for star formation, leaving behind dimmer remnants of their once bright selves. If this is the case, they may enter the Andromeda merger as ghostly, fading satellites, shadows of their former vibrancy. But there is another possibility. Because the LMC in particular is so massive, it may not be destined to remain a satellite indefinitely. Its orbit is decaying, and many astronomers think that in about 2 to 3 billion years, long before Andromeda even arrives, the LMC could merge directly with the Milky Way. If that happens, the story changes dramatically. Instead of being swept into the Andromeda collision as a separate companion, the LMC's stars and gas would already be blended into the Milky Way's disk and halo. In a sense, the Milky Way would enter its grand collision already swollen with fresh material from a smaller merger. The SMC, being less massive, might follow the LMC into the Milky Way as well, getting dragged along in its gravitational wake. If this sequence plays out, the Magellanic clouds as distinct entities will not survive to witness the great Milky Way-Andromeda union. Yet, if the LMC and SMC manage to persist as separate galaxies until the collision begins, their orbits would be reshaped in dramatic ways. The combined gravitational pull of Andromeda and the Milky Way would likely fling them into new paths, tossing them into eccentric loops, or even ejecting them into intergalactic space. In some simulations of galaxy mergers, satellites are not gently absorbed but rather hurled away at high speed, victims of the shifting balance of forces. It is not impossible that the Magellanic clouds could end up exiled from both galaxies, drifting into the wider local group as free-floating dwarfs, no longer bound to a single parent. Another possibility is that they might be captured by Andromeda rather than the Milky Way. When two galaxies merge, their stars and gas are mixed in a chaotic process, but satellites can sometimes switch allegiance depending on how the gravitational tides unfold. The LMC, for example, could end up orbiting the newly merged Milky Way galaxy, our future combined system of the Milky Way and Andromeda, but on a path that is more influenced by Andromeda's core stars than by the Milky Way's original structure. The clouds would then live on, but as absorbed fragments of a system much larger than anything they have ever known. Galaxy collisions are not like car crashes. Stars almost never physically hit each other because the spaces between them are so vast. Instead, what happens is a violent reorganization of orbits and gas. When large supplies of gas are funneled into the centers of galaxies during mergers, they can trigger starbursts. The LMC and SMC are both rich in gas. If they still hold onto their gas when the merger occurs, they could act like reservoirs feeding the starbursts that will blaze during the Milky Way-Andromeda collision. In this way, the Magellanic clouds might fuel some of the most spectacular light shows of the future night sky. The LMC in particular seems to sit inside its own dark matter halo, making it sturdier against tidal destruction than other dwarfs. If this halo is as massive as some measurements suggest, it could give the LMC extra resilience during the merger. While many smaller satellites may be shredded into streams and faint debris, the LMC could remain a coherent structure for much longer, possibly surviving as a distinct core within the merged Milky Way galaxy. If so, billions of years from now, astronomers living inside that distant future galaxy might still be able to trace a remnant of the Magellanic clouds hidden within the grander system, like fossils embedded in rock. While we cannot yet say with certainty which destiny awaits them, the fact that they are large and active makes their role in the future cosmic story particularly fascinating. Billions of years from now, when the Milky Way and Andromeda collide, the skies above Earth, if Earth is still here, will be filled with dazzling displays of starlight. Among the many stars swept into new arrangements will be the stellar legacies of the LMC and SMC. Can dwarfs escape their masters? The relationship between a giant galaxy and its smaller satellites is often pictured as one-sided, with the big galaxy pulling its companions inward, stripping them of stars and gas, and eventually absorbing them. But nature is rarely so simple. Gravity may be a dominant force, yet it is also dynamic, changing in response to motion, encounters, and cosmic timing. This means that satellites are not always destined to fall. Some may gain enough speed to slip free of their host's pull. To understand how a dwarf galaxy might escape, one first has to consider the concept of escape velocity. Every massive object creates a kind of invisible boundary defined by how much energy it takes to get away from it. For Earth, rockets must reach about 11 kilometers per second to escape the planet's gravity. For the Milky Way, the escape velocity near the Sun's location is around 550 kilometers per second. A dwarf galaxy, bound in orbit, typically moves well below that speed. Yet under certain circumstances, gravitational boosts can push it higher. The question becomes, where could that energy come from? One obvious source is interaction with another galaxy. When two giants merge, their gravitational fields overlap and evolve in chaotic ways. Satellites caught in the crossfire may find themselves accelerated as the balance of forces shifts. Some will be pulled deeper into the centers of the new system, while others may be thrown outward. Computer simulations of such mergers have shown satellites being flung into intergalactic space, stripped away not by destruction, but by velocity. They continue on as rogue dwarfs, no longer orbiting a larger master, but drifting through the void. There is also the possibility of a slingshot effect. In a way similar to how spacecraft use planetary flybys to gain speed, dwarfs can receive a gravitational assist when they pass near a massive companion. If the geometry is right, this can add to their orbital energy rather than subtract from it. Instead of spiraling inward, the dwarf picks up speed and shifts onto a wider, more eccentric path. In extremely rare cases, that path may lead to escape. It is worth noting that this mechanism is not theoretical alone. Astronomers see the same effect when small galaxies pass near each other, with one tightening into the orbit of the giant and the other being sent away at higher velocity. Evidence for potential escapees has appeared in the study of high-velocity galaxies. In a few regions of the nearby universe, dwarfs have been detected moving at speeds too high to remain comfortably bound to their supposed hosts. For example, in surveys around galaxy clusters, some dwarfs appear to be on paths that will eventually take them out of the cluster altogether. Clusters are extreme environments, far denser than a single galactic halo, but they provide a useful analogy. If dwarfs can be ejected from clusters, there is no reason they could not also be ejected from individual galaxies under the right conditions. For decades, astronomers debated whether the LMC and SMC were long-term satellites of the Milky Way or more recent arrivals passing through for the first time. Measurements of their proper motion with the Hubble Space Telescope suggested they are moving faster than expected for a deeply bound system. Some models propose that the clouds may eventually escape the Milky Way's grip, depending on how their orbit evolves and how dynamical friction slows them down. If they do remain, they will likely merge with the Milky Way. If they do not, they could become wandering galaxies of their own before eventually being captured by Andromeda or cast into open intergalactic space. A dwarf's ability to escape is closely tied to how massive and extended the halo really is. If the Milky Way's halo is larger than expected, escape becomes much harder. If it is smaller, more dwarfs could find their way out. Current models of the halo are still uncertain, which leaves the question of ejected dwarfs open. Even if the dwarf itself does not escape, parts of it can. Stellar streams can persist for billions of years, wandering through the halo and sometimes even leaving it. In time, they may seed faint intergalactic structures, remnants of galaxies that once orbited but then unraveled. In the early universe, when galaxies were smaller and more numerous, encounters were more common. Dwarfs may have been thrown around much more often, shuffled from one host to another, or set free into the void. Some of today's isolated dwarfs might be survivors of those ancient expulsions. They no longer carry the memory of their original masters, only their own faint light drifting far from the nearest giant. The possibility that these galaxies exist challenges astronomers to look for patterns. Are there too many lone dwarfs to explain by standard formation theories? Could a significant fraction of them be escapees rather than original independents? If dwarfs can escape the Milky Way or Andromeda, they do not necessarily vanish from the cosmic stage. Instead, they may linger in the gravitational reach of the local group as a whole. In this sense, escape is relative. A dwarf may leave the Milky Way's halo, but remain bound to the larger structure that includes Andromeda and Triangulum. Over billions of years, such dwarfs could be recaptured, joining new hosts, or remaining as free-floating members of the local group's population. The future of dwarf galaxy studies with next-gen telescopes. In the coming decades, dwarf galaxies may move from the sidelines of astronomy to its very center. For much of the last century, they were treated as curiosities, too faint, too fragile to be more than supporting characters in the grand drama of cosmic structure. Yet again and again, they have proven to be key players. The challenge has always been finding them, but with the rise of next-generation telescopes, the shadows will be pulled back. Soon, astronomers expect to uncover not dozens, but perhaps thousands of new dwarfs, each one a clue to the hidden history of the universe. The first revolution will come from the Vera C. Rubin Observatory, formerly called the LSST. This facility will map the entire visible southern sky in unprecedented depth. Unlike surveys of the past, which targeted particular regions, Rubin will sweep the whole panorama again and again over a decade, producing a living movie of the cosmos. For dwarf galaxies, this is a goldmine. Many of the faintest dwarfs remain undiscovered, not because they are too far away, but because they blend into the background. Their stars are too few to stand out individually, and their overall brightness barely rises above the night sky. But when a survey like Rubin's collects images over years, the faint signal can be teased from the noise. The hope is that what now looks like empty space will suddenly be revealed to contain countless hidden structures. Astronomers expect Rubin to uncover the faintest known galaxies in the local group, perhaps approaching the very edge of what counts as a galaxy. Rubin's census could tip the balance. If it finds them in large numbers, the current models stand. If not, the universe may be telling us something deeper. Rubin will not work alone. Another major player will be NASA's Nancy Grace Roman Space Telescope. While Rubin is a ground-based surveyor, Roman will operate from space, providing sharper views unobstructed by Earth's atmosphere. Its wide-field instrument is designed to image enormous swaths of sky at Hubble-like resolution. This means Roman will not only confirm dwarf candidates spotted by Rubin, but also reveal detailed structures within them. Faint stellar streams, central clusters, or signs of recent interactions could all be traced. Roman will also look further afield, beyond the local group. With its reach, astronomers expect to spot dwarfs orbiting galaxies tens of millions of light-years away, allowing us to see whether the patterns we observe locally hold across the wider universe. Together, Rubin and Roman will create something like a two-part system, one scanning broad and deep from Earth, the other zooming in from space. Add to this the James Webb Space Telescope, already operational, and the picture becomes even richer. Webb, though not designed as a survey telescope, can probe the inner lives of dwarfs with infrared sensitivity, peering through dust and catching the faint glow of ancient stars. Already, Webb has begun to uncover distant galaxies so small they resemble early dwarfs, offering a glimpse of what the universe's first building blocks looked like. In the future, Webb could be used to study nearby ultra-faint dwarfs in exquisite detail, especially their stellar populations. Beyond these flagship observatories, many other projects will contribute in vital ways. Radio arrays like the Square Kilometre Array will map hydrogen gas, revealing how much fuel for star formation dwarfs still carry and how that gas is stripped away by larger galaxies. Extremely large telescopes, or ELTs, on the ground, with mirrors over 30 meters wide, will let astronomers resolve individual stars in distant dwarfs, turning smudges of light into detailed stellar systems. Even high-energy observatories may weigh in, studying how supernova and black holes within dwarfs influence their structure and survival. One of the most exciting possibilities is that Rubin and Roman will find whole new classes of dwarfs we did not know existed. There could be galaxies so diffuse that their stars are spread over vast distances, looking like loose associations, until careful surveys reveal their dark matter halos. There might be gas-rich dwarfs hidden behind dust, or relic galaxies that never grew beyond their original burst of star formation. Another area where next-gen telescopes will shine is in tracing the dynamics of dwarfs. By watching stars move within them, astronomers can measure how much dark matter is present and how it is distributed. The same telescopes may also give us the first glimpses of star formation in the tiniest possible galaxies. Do ultra-faint dwarfs still form new stars today, or did they stop billions of years ago? If some remain active, they could challenge our ideas about how galaxies regulate themselves. If they are universally quiescent, that too would be revealing, showing that there is a lower limit below which star formation cannot persist. Understanding this threshold will help refine our models of how galaxies die. If dwarfs Ryanized the early universe, as many suspect, then mapping their modern descendants is like piecing together the family tree of the cosmos. Each faint smudge is a survivor, carrying the memory of an age when galaxies were newborn. By studying them in vast numbers, astronomers may reconstruct how the first light spread across the dark universe. The future is therefore one of abundance. Instead of struggling to scrape together a few faint dwarfs, scientists may soon have more than they can easily catalogue. The challenge will shift from discovery to interpretation, how to fit thousands of small galaxies into a coherent story of cosmic evolution. But that is a challenge astronomers are eager to face, because every faint galaxy carries with it a secret about where we came from and where we are going. Do dwarf galaxies challenge our definition of life-friendly galaxies? When people imagine galaxies that might give rise to life, they tend to picture grand spirals or sprawling ellipticals with billions upon billions of stars. These giant structures feel like the natural candidates for hosting complex chemistry, planets, and perhaps even civilizations. Their vastness provides both diversity and stability. Countless stellar systems, some violent, others quiet, spread across a disk or spheroid, where gas and dust recycle endlessly. But dwarf galaxies, with their fragile bodies and sparse populations, paint a very different picture. They are stripped-down environments, often shaped by the whims of larger galaxies. They have fewer stars, less shielding against radiation, and more chaotic histories. And yet, could life emerge within such tiny and harsh settings? The first hurdle is simply the matter of numbers. A galaxy like the Milky Way might have several 100 billion stars, giving it countless chances to form Earth-like planets in stable orbits. A dwarf galaxy might contain only a few million or even a few 100,000 stars. That means the odds of having multiple long-lived Sun-like stars are already dramatically reduced. Ultra-faint dwarfs often host nothing more than ancient dim stars. With so few potential homes, the probability of life starting somewhere seems lower. But reduced chances are not the same as impossibility. Even one star system with the right chemistry could be enough. Life as we understand it depends on a mix of elements. Carbon for complex molecules, oxygen for water and respiration, nitrogen and phosphorus for biochemistry, iron and magnesium for planetary cores and biological functions. In the Milky Way, these elements are the result of billions of years of stellar recycling. Massive stars explode, scattering heavy elements across space, which later seed new generations of stars and planets. Dwarfs, however, struggle with this process. Their small gravity wells mean that when a supernova erupts, much of the material is blown away into intergalactic space rather than retained. As a result, many dwarfs are chemically primitive. They remain locked in a kind of early cosmic state, with stars that contain only traces of heavier elements. This poses a clear problem for habitability. Planets are harder to form without heavier elements, since rocky material comes from those very ingredients. Gas giants would still arise, but stable rocky worlds with atmospheres and oceans may be rare. The smallest dwarfs could be nearly devoid of rocky planets altogether. And yet some intermediate-sized dwarfs show evidence of ongoing chemical enrichment. Within them, astronomers have found planetary nebulae, clusters, and even stars, with more substantial metallicity. This suggests that, at least in larger dwarfs, the ingredients for rocky planets exist. Dwarfs often lack the thick layers of gas and dust that shield larger galaxies from bursts of energy. Their stars are more exposed to intergalactic cosmic rays and to the fierce winds of their own stellar populations. In particular, many dwarfs contain high numbers of massive, short-lived stars. These stars can flood their environments with ultraviolet radiation, stripping atmospheres from nearby planets. A world orbiting within such a neighborhood might struggle to maintain liquid water or a protective atmosphere. Life would be pushed underground, underwater, or into rare sheltered environments. Still, one must not dismiss the protective niches that could exist. Not every part of a dwarf galaxy is equally hostile. Just as deserts on Earth do not prevent life from thriving in caves, oases, or shaded regions, dwarf galaxies might still harbor pockets of stability. A low-mass star, such as a red dwarf, could provide a long-lasting and steady source of energy. If such a star hosted planets, even in a chemically limited galaxy, the conditions for life might still emerge. Red dwarfs are common throughout the universe, and their extended lifetimes, stretching into the trillions of years, could allow biological processes far longer to develop than around stars like the Sun. Many dwarf galaxies are satellites, orbiting through regions where they are bombarded by tidal forces and stripped of gas. This stripping reduces the ability to form new stars and planets, but it also stabilizes their environments over long periods. Once a dwarf loses its gas and stops birthing massive disruptive stars, its remaining stellar population can quietly burn for billions of years. In such a frozen, quiescent state, small stars and their planetary systems might enjoy long epochs of calm. The galaxy itself may look dead, but on a planetary scale, life could have more than enough time to take root. Ultra-faint dwarfs preserve chemical records from the first billion years of the universe. If rocky planets managed to form in such galaxies, they would be ancient beyond imagination, older than the Earth by billions of years. Life in such places could be unimaginably old. It raises the possibility that the first stirrings of biology in the cosmos did not happen in large spirals like our own, but in these forgotten corners of the universe. On the flip side, the fragility of dwarfs might make them extremely vulnerable to catastrophic events. A single gamma-ray burst, supernova cluster, or even a collision with another dwarf could sterilize much of their limited star systems. Unlike the Milky Way, which can absorb such blasts without significant impact on habitability as a whole, a dwarf could see entire regions rendered lifeless in one go. The margin for survival is much thinner. Eventually, many dwarf galaxies may be shredded, their stars scattered into stellar halos, their gas absorbed into new star-forming regions. For life within such galaxies, this might mean the eventual destruction of any stable planetary orbits. However, once stars are stripped and join the halo of a larger galaxy, they may still carry their planets with them. Thus, the remnants of life-friendly conditions in a dwarf could persist, not within the dwarf itself, but within its captured debris inside a larger galactic system. The classic habitable galaxy model suggests that life requires size, stability, and heavy element enrichment, all of which favor giants. But the cosmos is more creative than our neat categories. Even within the harshest dwarf, a single star system might hold a stable planet with oceans, atmospheres, and biology. The chances are smaller, the risks higher, and the environments stranger. Yet if life is common, then it should appear in every kind of galaxy, not just the grand spirals. This makes dwarf galaxies fascinating testbeds for astrobiology. They show us the extremes of galactic conditions. If life can exist there, it may truly exist everywhere. If they turn out to be barren, their emptiness will highlight the importance of galactic size and chemistry in shaping life's cosmic stage. Today's journey comes to an end, but what other topic would you like for us to tackle? Send us your thoughts in the comments. And if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.